save it on the computer. So now you should see all on the top, it's recording. Okay, so I will admit everybody and then disappear. And you can start, Francesco and Carlos, okay?
Okay.
Fabio show up? No, not yet. Okay.
No.
Okay, he will.
Let's hope for the best. Okay, good luck.
Bye, thanks.
No problem.
Okay, so I guess we can start actually. It's 9:30, so yes, it's time to go. So good morning, everyone. So this is the very first session of the mini-colloquium Iontronics and the field effect control of semiconductor nanodevices. So the mini-colloquium will be chaired by myself, Francesco Rossella from Scuola Normale, and Carlos Leon from University Complutense. The colloquium consists in 2 sessions. One is today. The next one is tomorrow morning at the same time. And today we are going to have 3 invited speakers and 3 regular talks. Well, as you know, actually, if you have questions that you want to ask the speaker, please use the chat. So you can write your questions in the chat, and Carlos will manage the chat, and he will give the questions on your behalf at the end of the talk. So invited speakers have 25 plus 5 minutes for questions. Regular speakers have 15 plus 5 minutes for questions. Yes, I guess we can start. So here is the outline of today's session. Basically, the very first talk will be given by Adam Mikulic, Professor Adam Mikulic from University of South Wales. And the title of this talk is Integrated Proton Gating Bioelectronic Circuits using nanowires and nanoscale pattern and ion gating elements. So I guess we can start. Adam, the stage is yours.
Okay. Right.
I will. I should stop sharing my video. Okay, good. Oh, just last comment. So when 5 minutes, I mean, before the very last 5 minutes of the talk, I will just show up and tell you that you have 5 minutes. Okay.
Yep.
Okay.
I can see you, sir.
Yeah, I will speak, and you will hear me.
Yeah, I can see you on my second monitor. So it's
perfect.
Okay. All right. So just like to thank the organizers for inviting me to give a talk at the conference. It's a shame I can't make it to Spain because it would have been my first time there, but maybe sometime in the future. So what I'm going to talk about today is some work we've been doing with colleagues in Lund University, University of Copenhagen, and some colleagues at Swansea for quite a few years now, sort of building our way up from rather simple structures to some quite advanced sort of integrated nanowire soft material circuits in very recent times. So I guess where the sensible place to start here is sort of with a motivation, and I guess motivation for me in this space always was sitting between various material systems that I'd worked with at various points in my career, and seeing that different material systems have very desirable properties and wanting to put those properties together. And a motivator for me in a lot of this work has been on the semiconductor nanowire side, having structures with very highly exposed conducting channels that are very sensitive to surface effects. So with these nanowire structures, you've got material system with a very high surface to volume ratio where you can influence the conductivity externally very easily. And sort of these new materials that were coming sort of in the early 2010s, polymer electrolytes, where essentially you could drive ions remotely up against a surface and use that to influence the conductivity. And so what I really wanted to do was try and bring these two types of material systems together and get some functionality that you couldn't get out of either of them on their own. Given I've got the first talk in this colloquium, and there may be some people in the audience who are not entirely familiar with the topic, I might just give a very quick introduction to how this sort of material system works. And so you sort of start with a discussion of dielectrics almost immediately when you start to think about ionic gating effects for sort of nanoscale structures. And so if you go back to sort of early undergraduate studies, you start to learn very quickly that you can make dielectrics that are better than a vacuum by taking materials and relying on the fact that those materials like to form dipoles that polarize under a voltage. Basically what that does is give you an improvement in the capacitance that's based purely on properties of your material. And the one step that you have from this is to polymer electrolytes. And I always like to explain these to sort of, young students as imagine taking your conventional dielectric and being able to cut all the dipoles in half and let one side of the dipole run up against one surface and the other side of the dipole run against the other surface. Then you would have a very efficient material for transferring gate fields to your interfaces, and that's more or less what happens with a polymer electrolyte. You essentially have a dielectric that's dissociable that allows you to put your charge, your effective gate charge, right up against your interfaces and get you very, very strong fields and very, very strong gating effects as a result. Now, it's all well and good to draw a picture like this. What you're really looking at is something that looks a little bit more like a bowl of noodles. You've sort of got these nice long polymer chains that form to some extent a tangled network, in many cases that's cross-linked together. And then that material fills up essentially with water, and what you have is some dissociated ions, whether it's a salt that you add into that water or just dissociation of water into protons and OH minus. And basically those ions have to migrate through sort of this tangled matrix, and that ends up giving you one of the big issues that you have with a lot of these polymer electrolyte materials, which is that they can be intrinsically slow to respond simply because you need ions to diffuse through this very complicated network to get from one interface to another in terms of the device scale. So I came into this topic around about 2012 or so, motivated by some work from Juan Gao's group at Case Western Reserve University in the US. And they had this nice material system here where they basically took indium arsenide nanowire on a silicon oxide layer. And by doing a very short HF etch, they could basically dig out some space underneath that nanowire. And then they went and backfilled that space with polyethylene oxide lithium perchlorate mixture and used that to get extremely small gating voltages in this material system. So normally people who are used to working with nanowire transistors are used to having to put tens of volts on to go from on state to off state. All of a sudden you could, within the space of a volt or so, switch these devices from on to off state, very, very sharp gating characteristics. This was functional, but one of the problems that you could initially spot here is that you've got this very large blob of polymer electrolyte compared to the scale of the device. And these nanowire transistors, typically the channel length is of the order of 1 or 2 microns. And the other two dimensions here are, something between 50 and 100 nanometers as your two diameter directions. And if you have this big blob, you've kind of got this device where you're not able to independently control sort of multiple gates on a device, which would be desirable. You're not able to have multiple devices on a chip. And you also have issues with your source and drain contacts being connected to the same polymer electrolyte and dragging the sort of ion distribution around when you try to apply voltages to other parts of the device. And my background was very heavily in nanoscale fabrication. So what we wanted to do was try and take the sorts of techniques that you use to make nanowire transistors and see if we could bring sort of these ionic gating materials down to very similar scales. At the time, polymer electrolytes were really a thing that came from sort of organic electronics rather than sort of your hard silicon 3.5 semiconductor electronics. And in organic electronics, the real focus is on very low cost techniques that operate well on flexible substrates, and bringing scale down to very small scales is not really a big concern there. So at the time, the patterning of these sorts of polymer electrolyte materials was really limited to sort of, hundreds of microns, which is, 2, maybe 3 orders of magnitude larger than we would like it to be in order to make these compatible with nanoscale devices. So the first challenge we faced was basically to pattern these materials. And what we figured we might be able to do was to use them as their own electron beam lithography resist. There was some prior art in the literature to suggest that this might be viable. And the one thing that we were most concerned with was not whether we could pattern the material, but whether we could pattern it at the scale that we needed, and also with very high loadings of salt in order to get good ionic conductivities in this material, because we were sort of concerned with having very high ion densities that you would put electrons into this material system from your electron beam, and the ions, rather than causing cross-linking or chain breaking in your polymer, would actually just disappear into the salt. At first, we thought this was one of these experiments that you give to your PhD student. You say, I don't think this is going to work, but give it a try and we'll see how we go. And surprisingly enough, it worked immediately. Student came back 2 days later, hey, this works, it's great. We can get resolutions down to sort of, hundreds of nanometers. And so here was one of our first samples. Basically, what we did was take polyethylene oxide, make a solution of it in alcohol, spin coat it on like you would with a normal resist for nanoscale patterning. It's a negative resist, so where you write with the electron beam is where you have the material retained. And so we were able to write these nice stripes with limiting resolution of around about 400, 500 nanometers without too much problem. And with some good engineering of that material system, you could probably get even further down in line width here. And that's even with very high, 10% fractions of salt mixed in to that polymer electrolyte material. So just to demonstrate where you can go with this, this is now a nanowire transistor. We're using AFM rather than scanning electron microscopy to image this, simply because the polymer electrolyte now charges up and makes it difficult to get imaging under SEM. And so source contact, which is metal, drain contact, which is metal, semiconductor nanowire running through here. And rather than having one very large blob of polymer electrolyte on this material, we have a strip that's sort of on the order of a few hundred nanometers wide and a few microns long. And in here, we have it connecting 2 electrodes, mostly just so that we can demonstrate that it's not a conductive element in the system. So apply a voltage to the nanowire transistor, you get a current flowing through. This is this current up here. If you apply a voltage to either of these 2 gate electrodes here, you can basically make this device go from on to off in the space of about a volt or so, which is remarkably good for nanowire transistors. And just to demonstrate that this element is truly non-conductive, you can try and put a voltage between these 2 gate electrodes here, and you can see that the current that passes between them is essentially 0. Okay, and if you think about this just from a nanowire transistor perspective, this is really nice. You essentially get a wraparound conformal gate without the trouble of having to make a wraparound conformal gate, which if you're a device engineer is actually very difficult to do. And without having to worry about leakage from your gate to your channel, simply because your gate material is intrinsically non-conductive because it's using ions rather than electrons to work in here. So this is actually kind of rather nice structure. And more or less straight away, we were down at the scales where we could, in principle, make multiple independent gates to a device in here. And so these are now connected to individual electrodes just in here. And you can see either of the two electrodes that we run, we can switch off this particular device. And this dot dashed line running down through here is running both gates together, and we get a slight improvement in the performance if we run both rather than one, which is potentially just a stronger gating because you're cutting off more of the channel in the process of doing this. Okay, so this was a few years ago. One thing we tried at the time, which is interesting, we haven't pursued it since, but I'll mention it since it might be of interest to other people, is that these ionic gating systems tend to cease working if you take them well below the freezing point of water. And what you can do is basically take the temperature down to about minus 20 degrees Celsius, maybe a bit lower than that. Actually, it's probably a bit lower. It's maybe about minus 50, 220 Kelvin or so. And what will happen is the ions will lock into place and the polymer electrolyte will cease working entirely. With these nanowire structures, you still have a backplane that you can use as a gate in here. And so one nice feature you can do here is use your ionic environment to basically set a sort of almost like an external doping that's fixed on the outside and allows you to tune the threshold voltage of your transistor. And so basically, if you want to change the doping layout for your device, all you have to do is come back up to room temperature where the ions are mobile again, reconfigure your voltage to move the ions around, cool it back down below the freezing temperature and lock that charge in, and it reconfigures your particular device. So to demonstrate this in action, this is a little piece of work we did with Lund University. So this is your transistor characteristic at low temperature. So this is 275 millikelvin, so low temperature device here. And in a lot of cases, nanowire transistors are of interest for sort of quantum scale devices. So these sorts of temperature ranges are quite useful for applications. You've got this nice long curve down here where the current drops all the way out to zero. These fluctuations in here are just sort of quantum interference effects. What's important here is where this device switches off. And so for the remaining traces on here, I've gotten rid of this higher data to avoid obscuring the plot. But if you look at just this first section of trace here where the device switches from off to on, you can see here that we can move this essentially by coming up to room temperature, changing the gate, the voltage applied to the ion gel, and then cooling it back down again. And you can do this progressively. So you can move the threshold step by step in this device just by retuning this along. And this has sort of a nice linear dependence that you can use in here. So for one application of these sort of patternable nanoscale ion gating structures is you can more or less use them as sort of controllable doping for low temperature studies in devices in other material systems, if you're interested in going in that direction. We have been making a conscious effort recently to try and build applications that work more close to room temperature rather than low temperature. It's just an interest. We can't do everything, so we do some things. And one thing that we wanted to get to was being able to build complementary circuits. So we had a parallel stream in my research group where, in addition to looking at N-type electron channel indium arsenide nanowire transistors, we were looking at hole conducting gallium arsenide transistors. And one thing, we spent a lot of years trying to get this material system to behave very well. It's a difficult system to work with. And in the end, what we ended up with was something that was a little bit of a Goldilocks situation. We had to get the doping of beryllium in the gallium arsenide just right to get these transistors to work. And if we had not enough beryllium, the nanowire wouldn't conduct. If we had too much beryllium, the nanowire would conduct really well, but the gate wasn't able to switch the channel off. And if we had just the middle amount of beryllium in it, we got sort of an okay conduction in the nanowire, and we could switch the device on and off, but it wasn't very good. And this was sort of frustrating for us because we really would like the current performance that we got in the high doping with the gating performance that we got in the middle range doping. And one thing we decided to try just for a little bit of fun was to see whether ionic gating might be able to take the high dope device, which gives us very good current, but we can't switch off with a metal oxide gate, and see if we could switch that off with ionic gating. And it turns out quite nicely that this actually really works. So this is more or less one paper where the whole paper itself fits into one figure. If you take a nanowire transistor and try to use a conventional metal oxide gate on it, if you've got a very high doping in that channel, the current is very, very good. You drive your gate out to try and switch this off, and the gate doesn't do very much. If you do sort of an undergraduate device physics course, you learn very quickly that you can't make transistors out of metals because the voltage you need to deplete a metal is so high that your oxide breaks down. And sure enough, that's exactly what happens here. So if we drive this gate out to sort of 15 volts or so, it breaks down before you can pinch off conduction in this highly doped nanowire. If you take the same highly doped nanowire now and instead use ionic gating approach, not only can you get this to turn off, but something quite remarkable happened that we found, which is that you get very, very sharp gating in here. We can get to within about 20–25% of room temperature thermal limit gating performance on these structures simply by going across to ionic gating, okay? This might seem really appealing at first. The one problem that you have with using ionic gating is that it's not very fast. So you kind of hit a roadblock here in terms of applications, because usually for these sorts of nanowire transistors, you want to be able to do this switching quickly, and that's not something that works very well with ionic gating. But one of the nice aspects of ionic gating is that it actually sometimes does work in ranges where metal oxide systems are not very good. And so to come round to the main topic I wanted to deal with in this talk is we've sort of been looking very much recently at how to take these sorts of ionic gating systems and build them into circuits that enable us to essentially transduce ionic signals into electronic signals by taking a mixture of organic and inorganic materials. So what we can do is build a circuit that looks a little bit like this one up the top here. I've sort of drawn what I consider to be the ionic branch in red and the electronic branch in black. And so what we have here is essentially an electrode that connects to a polymer electrolyte gate to a p-type transistor, an electrode that connects to a polymer electrolyte that connects to an n-type transistor. These are in series, so we're essentially making an inverter. Or if we reverse those, we can make an amplifier out of this circuit. And while we've sort of done a trivial case here of just having, you know, a metal connecting to an ionic element connecting to an electronic element, you could imagine having instead the ionic elements coming out and putting, you know, for example, a neuron or something on there as some way of transducing ionic signals into electronic signals on the other side. And so what we can do is drive an input signal on this ionic side. And that's this square wave signal that you see just here, and use that to turn into an electronic signal on the right hand side in this inverter circuit here. And so this is the black data that you see in this diagram here. And so we can make very simple inverters and push-pull amplifiers out of this. And when we first did it, what we did was basically take our individual polymer electrolyte N-type transistor, our individual polymer electrolyte p-type transistor, connect them together in an external circuit and try to make this work. And we had a number of problems with doing this that meant that in addition to having no gain, which is not very good for a circuit, because usually if you want an amplifier or an inverter, you want gain that's greater than 1, we also had very poor time resolution. And so at that point, it set us up a few major challenges, which were one, we had to get better performance out of our p-type transistors, which I more or less talked about in the last slide, going to increasing the doping to get that out. The circuits were non-monolithic, and so ideally you would like these to be on a single chip, which we've now done. And the other problem we had here is that polyethylene oxide, which was our chosen polymer electrolyte at the time and has been used quite heavily, has a rather slow response and a limited frequency range. At best, we could operate these transistors up to about tens of hertz before we sort of started to lose the signal. If you look in the literature, there's a number of suggestions on which ways you can go to improve this gate speed issue. And one of those is to go to ionic liquids and gels. And there's been a little bit of work done on this by Francesco's group. I'll let them talk about it. I just want to point out that that's one route that you can take to do this. We went for an alternate plan here, which was basically to try and find a material that still was a polymer electrolyte rather than specifically an ion gel. So I guess the difference between ion gel or ionic liquid is essentially it's a salt that dissociates at room temperature into a liquid. Polymer electrolytes, you kind of have this polymer backbone with water absorbed inside, and you have dissociation of a salt into that water. So that's sort of my separation of the two materials. We kind of wanted to stay with polymer electrolytes rather than move to ionic liquids, mostly just because we could, and mostly because we had an idea of where we might go with this, which was to try and find a polymer electrolyte material that had a much higher conductivity. And the thing that we found when we went into the literature is a material called Nafion that gets quite heavily used in fuel cells as an ion exchange membrane. And it's a popular material in that application because it has a very high protonic conductivity without needing to load it up with salt. Essentially, the way I like to colloquially think of it is essentially it's Teflon with sulfonate groups attached so that it forms sort of this nice structure with water pores through it, where ions can migrate at very high speed through those pores inside that material. You buy it as pre-made membranes, and you can take those pre-made membranes and you can dissolve them into sort of higher order alcohols like propanol, and spin coat that material onto surfaces. So what we set out to do pretty quickly with this was try and do electron beam lithography with Nafion in the same way that we did it with polyethylene oxide. And it turns out that works quite well and pretty much straight away. So you can basically take Nafion, dissolve it in alcohol, spin it as though it's a normal resist, write patterns into it with an electron beam, and then dissolve away the unpatterned Nafion. In this case, we use a mix of 1-to-1 acetone to propanol as our developer agent. With polyethylene oxide, that's usually water that we use as the developer. Again, we get quite nice line widths in here for this material. So you can see we can make structures, of order length 10 microns, line widths down to sort of hundreds of nanometers or so, depending on how thick the film is. And we can make these in such a way that we can have separate stripes in rows that are essentially ionically isolated from one another. One of the things that I will warn about with Nafion, and we didn't expect it to happen when we found it, is that Nafion eats nanowires. We didn't expect it, but now that in hindsight, knowing a little bit about Nafion, we probably should have expected it. Nafion is a material that's basically called a superacid catalyst. It basically likes to dump lots of protons into the material. And so it creates a very acidic environment that for particularly nanowires that are connected to metals, because you get a sort of metal-assisted etching, but even nanowires that are not connected to metals, over time you get a sort of erosion or acidic degradation of your nanowire inside that Nafion material. And it was particularly bad if we had contacts deposited onto the nanowires before we put the Nafion gate in. And so we basically had to change our entire fabrication strategy to make these, because in the original set of devices we made with polyethylene oxide, the polyethylene oxide was the last material we dealt with. in the fabrication process, and that was because it was water soluble. Water soluble, but also alcohol soluble. So every other process in the fabrication route would destroy polyethylene oxide. One nice aspect of Nafion here is that it's more robust than polyethylene oxide. It's not soluble in water. Once it's patterned with an electron beam, it's not very soluble in the developers for all of the other resists that you use for device fabrication. And so we ended up changing our process to one that looks a little bit like this. We put our nanowires on our surface first. We then write and develop our Nafion elements directly onto there. We can do that then so that there's no metal on the chip that drives the etching of the nanowires via the Nafion. We can then go back and do our metallization structures for the device with Nafion remaining. You can't do this with a lot of polymer electrolytes like polyethylene oxide because they're soluble in the solvents used for photolithography and electron beam lithography. And you can do multiple steps of metallization to do this, to basically build up an integrated circuit structure. So here's the final device just here. There's a P-type nanowire and an N-type nanowire in here. Those are separate depositions from sort of a gallium arsenide growth and an indium arsenide nanowire growth, which we position using a micromanipulator system. And then we pattern the Nafion structures, so you can see them as the little purple bars just extending out from where the nanowires are. And then we write the rest of the circuit in here. And so you can see we've kind of got this inverter circuit in here. So your drive goes in through here, down through the P-type, out through the N-type to drain. And then you've got your gate electrodes to the Nafion elements just in here. And the output just down in the corner. So these devices actually work quite well. The Nafion-gated indium arsenide nanowire transistors, as long as you have the Nafion well hydrated, are quite well behaved. You get reasonably good gate voltage characteristics for them with reasonably good current. As we found with our earlier devices, the performance for the indium arsenide is a little better than the gallium arsenide. And so if you were an engineer, you would really be working on trying to engineer the performance on the gallium arsenide side for these devices. And the hydration for these is very, very important. If you don't have a lot of water in that Nafion film, it doesn't gate very well. But that's okay for sort of bioelectronics applications because you're usually going to be in wet environments anyway. The one nice thing about these structures now is that we can get gain greater than 1 out of our circuits in here. So we get gains sort of up around 5 or 6, which compares reasonably well to either all organic circuits using ionic liquids or all inorganic circuits using nanowires. Okay, so we sort of compete well with all organic and all inorganic in mixing these two materials together. But the big place where we get gain is in AC performance. So this is now looking at input signal here in purple and output signal here in sort of this cyan color. And you can see tens of hertz, we get reasonably good response. 100 hertz, we're still okay in here. And even up into the sort of hundreds and kilohertz, we're still getting a response out of our circuit in here. Just for quick comparison, if we were doing this with polyethylene oxide, we would be sort of a rough wiggle just in here and flat line for both of these 500 hertz and kilohertz signals. But if we put something in, the thing you have to realize with square waves is square waves are essentially a Fourier sum of sine waves of much higher frequencies. So when we put in a square wave at 1 kilohertz, we're actually putting in a whole part of spectral content that's up well above 1 kilohertz. So if we put in a drive signal, it's just a sine wave here, just to look at sort of basic response to this. You can see that we get reasonably good sine wave response out of these at 1 or 2 kilohertz still for these Nafion structures that we have in here. Probably a good 1 to 2 orders of magnitude better performance for our Nafion structures than we have for the polyethylene oxide devices. And I think I might finish with just a quick where you could go with this. One place that we're interested in going is actually scaling down Nafion as a device material, not just as a gating material, but potentially also as a sort of protonic device material. So a few years ago, there was some interesting work from Marco Rolandi's group looking at essentially trying to make protonic transistors where the charge carrier is actually protons, not electrons. So what they had was palladium hydride as the source and drain contacts. And you basically get this by taking palladium metal and exposing it to hydrogen gas. The hydrogen gas dissolves into the palladium metal. It switches from a metallic looking contact to a sort of white, non-metallic looking structure. And then you can apply a voltage across here and basically drive protons to move through this Nafion. And one of the challenges you have with these sorts of structures is that the migration of hydrogen in the palladium is not quite fast enough to keep up with the migration of protons through the Nafion material. So you actually end up getting sort of depletion of your material at the contacts. And so you're not able to essentially drive these at AC or at DC, sorry. You can only really drive them at AC because of this depletion effect. And you can sort of drive this depletion from one side back and forwards between the two sides of these devices. These were actually macro scale devices. They were quite large. And so what we were thinking of doing was basically trying to take these down to a small enough scale where we might be able to deal with volumes of material and interfaces where we overcome that blocking and depletion at the contacts issue. And that becomes something you can realistically do when you can take sort of, Nafion and pattern it at sort of nanoscale structures using methods like electron beam lithography. So I think I might finish there because I'm probably 1 or 2 minutes away from Francesco sticking his hand up, and just thank a number of people who've been involved in the work. My research group at the moment is almost entirely had a little bit of a role to play in this. Roman did some of the early work with Nafion before he took up a postdoc in Lund, so he did all the early patterning of Nafion. And then Jan, Jakob and Key have sort of all worked together to make the whole circuits fit together and work and characterize Nafion as a material. We'll have some follow-up papers coming once we get the inverters paper through, looking at how the performance of Nafion as an electronic material depends on exposure to electron beam, exposure to water in the atmosphere, exposure to hydrogen, and those sorts of things. And the other thing I should really mention is a big collaboration I have with Paul Meredith in Wales on Nafion and ionic gating materials. He was the one person who really got me interested in sort of heading in Nafion as a good direction to go in. And we have some grants together to work on this as a material system. And a whole bunch of funding agencies, including collaborative partners in Denmark and Sweden. Thanks for your attention.
Thank you very much, Adam, for this fantastic talk. Actually, so let me ask Carlos if we have few questions. Yeah, so one question.
Yes, there is one question from Dominic Pertit. Is it possible to improve the efficiency of Nafion by using dissolved salts rather than humidity?
Potentially, yes. We haven't tried it. And I think we haven't tried it not because there's no reason to. I think it's just with any research project with a handful of students, there's a finite number of things that you can try all at the same time. And we've sort of had our work cut out for us just characterizing it in terms of humidity and also hydrogen. But I would still suspect that you still need reasonably good hydration of the Nafion, even if you add salt, in order to have that salt dissociate and be mobile inside the Nafion. If you look closely enough at sort of the materials aspects of polymer electrolytes, One of the key things that water coming into the system does is it causes the material to swell, particularly with polyethylene oxide. But also, we're trying to get a good understanding of how much that matters with Nafion as well. We've got a partial data set for that at the moment. But in both cases, what you really have happening is your material sort of expands a little bit to soak up the water, and that is what enables your ions to move through that material well. So I think in either case, whether it's Nafion or PEO, you really need to get the water content high.
Thank you. Well, actually, I have a. Oh no, there is another question.
Another one.
Yeah.
Do you suspect that this swelling may induce a strain on devices?
In the configuration we're in, probably not significant enough that it matters too much. But I could imagine creating systems where it does matter. And we've thought a couple of times about whether you might be able to, for example, make a capacitor, and by measuring the change in capacitance, for example, measure the swelling in that sort of way. You could imagine doing that, yeah.
And one final question from Elias Torres. Is it possible to pattern those polymer with UV lithography instead of electron beam lithography?
To the work we've done so far, no. And the reason there is that if you wanted to do UV lithography with these, you would basically need a cross-linking agent that's UV activated, because what we're doing with these materials is using them as negative resists. And when you've got a negative resist, you're basically causing a cross-linking. That's how you get the contrast. The nice thing about electron beam lithography with these two materials, and if you've done a lot of electron beam lithography, the dominant resist is polymethyl methacrylate, and it's actually a positive resist. It's the exact opposite. So what you do there is you break the chains rather than make the chains. We're relying here on some good fortune of just polymer chemistry, that these materials like to cross-link when you hit them with an electron beam. For polyethylene oxide, it's reasonably well understood what the chemistry for that is. For Nafion, it's not yet, but the early evidence we have suggests that what happens is you break the ether bonds in the side chains for your Nafion. So let me just pop back a few slides to where I've got the chemical structure. So there's a couple of ether bonds just in the side chain for the Nafion. And so what we think happens is that those get broken by the electron beam, and then they end up cross-linking either to the adjacent chains or to a broken bond somewhere on another backbone, and that's what gets you your contrast in the material. So at the moment, UV no without doing some chemistry.
Okay, so I guess we are, well, I had a question as well. If you can just spend a few words about this idea of combining organic ionic systems with nano devices, I mean electronic nano devices. If you can spend a few words on your research activity in this direction, but just, we are a bit running out of time, so maybe just a couple of minutes.
I can see the chat, and so one of the questions in the chat actually hits one place where we have been thinking of going, which is essentially using it as a biological to electron transducer. Essentially, we want to be able to measure ionic environments in some way, whether they're at cell level or below, and turn them into electronic signals without having to expose those biological environments to materials that are not very nice, like indium arsenide and gallium arsenide. So in some respects, we're trying to get a biocompatible interface, or a more biocompatible interface to nanowire transistors in some ways. Nafion's a bit of a challenge there. It's not completely toxic from a biological perspective, but it does give you a very acidic environment. But the one problem we are finding, and we have had issues with, is just it's very aggressive to the opposite direction, the electronics side. And we need to do a little bit of work on how to make devices more stable. So our polyethylene oxide devices would last forever. Like, we pulled out some that we'd made years ago and put them back in to test them again, and they still work. The Nafion devices, unless you store them under a vacuum, they don't survive very long in ambient environments. And that's probably a big issue for Nafion as a material. And ultimately, people might end up having to head towards some sort of middle ground where you have a material that's a bit more stable than PEO from a fabrication perspective and a bit less acidic than Nafion from a biological perspective. That might be a utopia, and that's sort of where we're thinking of doing some work in this.
I see. So
and separators and stuff are exactly the sort of games that we're thinking of on this. Being able to put nanoscale patterned. So one thing we'd like to do is actually be able to see if we can do multiply patterned materials with EBL in stacks and stuff like that. There's a lot of nice little fabrication challenges in this topic.
Yes. Okay, Adam, thank you very much for your contribution. And okay, so I guess we are a bit running out of time, so let's move to the next invited speaker. He's Fabio Cicoira from Polytechnique Montreal, and Fabio is going to give a talk on flexible, stretchable, and healable electronics. So if you are with us.
Good morning. So I apologize, it's very in the middle of the night here, so I am not 100% awake. So I believe I have to share my screen. Just 1 second.
Fabio, are you with us? No.
I think he needed to restart the connection because it's the first time he sets up video sharing. So
let's wait for 1-2 minutes, hopefully no more. Then maybe in the worst case, Carlos, what do you think? We can move to the regular talk by Dominic in case Fabio has big issues. But let's wait for a couple of minutes.
Yes, we can wait for a couple of minutes.
Hello?
Hi.
I think you need to enable share screening.
Yes. You should use the sharing screen option, Fabio.
Yeah, but it's written that it's disabled by host.
Okay, so Lola, maybe you can give a hand.
it is already, you are co-host. You should be able to share your screen now.
Let me try again.
Yeah, perfect. Here we go.
Okay. Okay, so apologize again. So the title of my talk is Flexible, Stretchable, and Healable Electronics, and I am a faculty at Polytechnique Montreal in Canada. So my work is about conducting polymers, and I just want to spend a few words to say why I like to work with this material. So first of all, it's important that with this material we can work in aqueous environment, and this is very advantageous if we want to interface these systems with the biological system. Then we have in this kind of materials, in contrary to what happens with some other materials, we have oxide-free interfaces. So we have, even if we work in a liquid environment, we don't have corrosion. Then, since we are working in iontronics or bioelectronics, we have in these materials both ionic and electronic transport, which is also an advantage to work when we work with biological system, and as I will try to show later, is also a method to decrease the impedance between a device and a tissue interface. Then, and this is probably the most important topic of my talk, is that we can optimize or tune the mechanical properties of these materials through processing. And this allowed us to obtain flexible, stretchable, and healable films, which is not always possible with other kind of materials. Then there are other advantages like processing at low temperature, versatile processing. I mean in this way that we can process these materials in many ways, from spin coating to printing to in situ polymerization. And then also we can also work on the synthesis to achieve tunable electronic or also optical properties. Then another important point, which is often neglected, is that these materials, they can switch from a conductive to a semiconducting or insulating state by electrochemical switching, and this switching is gradual. So we can have a material which is, let's say, very conductive without any applied bias, but it can become less conductive when we apply bias, and this transformation is gradual. It's not an on-off transformation. Then another point is that, so of course there is still a lot of work to do in this material, and most of it is about the processing and understanding of fundamental properties. Okay, so the mostly used material in the field of conducting polymers, the one you are seeing now, it's polyethylene dioxytyrene doped with a polystyrene sulfonate. It's only one conducting polymer that it has been very successful for several reasons. First of all, because since many years it's commercially available, and actually its performance is very good in terms of conductivity, processability, also stability in water. So of course you can make your polymer yourself. There are other advantages to make your own polymer, but it's now very advantageous to use this formulation because it's available commercially. There are several formulations that are available where you can find optimized conductivity, printability, or optical properties. And the advantage of having this polymer is also that it's a water dispersion. And this means that we can mix it with other water-soluble materials or polymer to improve the electrical and mechanical properties. Just a few words about bioelectronics, even if it's not the main topic of my work today. So it's a discipline resulting from the merging of biology and electronics, and actually it's not a very new discipline because these devices are available since a long time. We can think about pacemakers, brain stimulators, also hearing aids, sorry, not hearing aids, but cochlear implants. And as I said, these materials are still are already available since a long time, but we still need to improve these materials. First of all, in terms of lifetime, in terms of quality of interface with the tissue, and also in terms of recorded signal, because of course, if we have a metal implanted in brain or in any other part of the body, there is a kind of degradation of the interface with time due to the corrosion, due to growth of tissues on the metal. And this leads finally to to a deterioration of device performance. So even in terms of recording and stimulation. And this is why we need to improve this interface. And this is one of the things that we are trying to do with conducting polymers. Unfortunately, this won't be the talk of today, but I think you have seen the news yesterday that also the company, which is led by Elon Musk, is very active in this field, a company called Neuralink. So, and I strongly believe that conducting polymers can help in this improving of interface. So we are working on this field since quite a long time. So in the beginning, we started to make flexible devices. This dates about 5 years ago. So what we did at that time, we built a flexible microtransistor on plastics. So we used the polyethylene terephthalate substrate, which is the most common plastic, which is also used for packaging. And by using photolithography, in this case, we changed a little bit the materials, as I will show you in a minute. We were able to build the transistors with a channel length as small as about 5 microns. It's not a nano device, but for photolithography on plastic, this is quite a remarkable result. So you can see here in the slide that we have gold pads with a distance of about 5 microns. And in between these pads, we can pattern the organic semiconductor. What we did here, we used another family of photoresists. We didn't use the traditional photoresists that are used in lithography, but we used the fluorinated materials. As you can see here in this slide, the reason to use that is that we don't want these materials to chemically interact with the organic material. So if we use traditional photoresist, this would significantly deteriorate the properties of the organic semiconductors. But as you can see here, the fluorinated materials, they are orthogonal to aqueous system, but also to oleophilic systems. So they are totally inert to organic materials, and they can be used to pattern any kind of motif with organic materials. So, of course, once we made these devices, we also took care of the fact that we wanted them to be flexible. So we did the bending tests, and we bended the devices many times, about 1,000 times, just by in the way we can see in the slide. We did it manually at that time, didn't have a tester. And you can see here that actually the current doesn't change into the device while the device is bent. So you can see here in magnified image, in magnified plot, that you have only a change of about 4% with respect to the initial current after 1,000 bending cycles. So this means that not only these devices can be made on flexible substrate, but they are actually flexible. Here the performance, so you can see here also, I can also explain here how this device works. So these devices are electrochemical transistors, so they are gated by an electrolyte. So you have simply the source drain, the active material, then you have the electrolyte and you have the gate. So this also makes the structure very simple because you just need to interface, for instance, an aqueous electrolyte, as we always do with in case of PDOT. And here you have the transistor characteristics. What is important here is that the operation voltage is very low. So they are operated between well below 1 volt. So this means that you don't have the risk of water electrolysis that thermodynamically occurs at about 1.2 volts. And what you can also notice here that these devices are depletion type transistors. So if you look at the curve at 0 applied gate voltage, you see that it's a kind of ohmic. I don't know if you see my cursor here, but it's the black one. And when you apply voltage, you decrease the current till, in theory, you switch off the channel. So in this case, if you want, this is a little bit a drawback, since most of organic conducting polymers are conducting in a doped state. So you can only switch this transistor off. You can only operate it in depletion mode. Now there are some new polymers that can also give electrochemical transistors operating in accumulation mode, but with the PDOT we are limited to depletion mode. So on the other side of the slide, you can see the transfer characteristics, which also show you that the transconductance is relatively good, and also the on-off ratio is about 1000, which is not bad for an operation range below 1 volt. Then we can also show that we don't have much hysteresis, and that if we cycle the devices a few times, the performance stay unchanged. So the key here is low voltage, stable and cyclable devices, and operation on plastic devices. Then, after having done flexible devices, we move to stretchable devices. And one of the reasons is that we want to have also electronics that can be placed on the skin, so that can be deformed and fall of the deformation of the skin without undergo any performance deterioration. Here it's just an example of how the skin can be stretched. This is a very old graph. It's about the skin of sheep, I believe, but it doesn't change too much. Our skin is stretchable up to about 30–40%. So what we want to have is that we would like to have devices that could be placed on the skin, be stretched about the same amount of the skin without undergoing any electrical deterioration. So we have achieved these stretchable devices in a few ways, and I will quickly show how we did that. So one is substrate buckling. So we work essentially on the elastomeric substrate, then tuning the film thickness of the organic semiconductor, and also the last approach, which is probably the most interesting, is to blend these materials with other non-conductive material, but that can change the mechanical properties. So since the beginning, we worked on, we used the polydimethyl siloxane, so PDMS, which is one of the most widely used elastomers for a laboratory application. It has several advantages. It can be tuned in thickness. Also, it can be found commercially and prepared in the lab. Of course, we are now looking also at other materials. And of course, when we moved to this kind of substrate, we also had to engineer a little bit the processing of the devices, because it's not you cannot apply conventional lithography processing on the elastomeric substrate, because they are not really compatible with the traditional lithography. So what we did in this case, we first patented the metallic electrode. This is still, again, something that we have to do, because when we make devices, when we have to make contact, we still have to use metals. We didn't find a substitute yet, even though there is a lot of work on printed silver electrode, but still the performances are not comparable to metal. So this is also something we would like to do in the future, to move away with this contact. But anyway, in this case, we had to patent gold, and I will show you in a minute how we did it. And then we patented again the channel, the organic material, again by using the approach that I just showed for plastic substrates. So this is a little bit in a very synthetic way our processing. So as I said, this first approach is based on substrate buckling. So what we did, we make first a quite thin film of PDMS, of elastomer. What we do during the processing, we keep this device under tension. So we stretch the film, we apply a mechanical stress on the two sides of the film to pull it. Then we do all the processing on this pre-stretched substrate. So we start by depositing gold, then we deposit the conducting polymer, and at the end of the process, we release the stretching, and we obtain what you can see here in the scheme, a kind of a wrinkled structure. And on the right here, you can see the advantages of this configuration. If you look on the top, there is a plot of the current versus strain. This is for a buckled substrate. You can see that if the substrate is buckled, you can actually apply 40 or even about 50% strain on the device, on the substrate, on the film, without seeing any change in the current. So this means that by modifying the substrate properties, you actually achieve a device which is stretchable. And you can see also on the lower part of the graph that this these stretching cycles can be repeated up to 1,000 times without seeing any significant change in the current. Here is a little bit again about fabrication. So pre-stretching, deposition of gold, we have to use a kind of a process involving Parylene shadowed mask. I don't know if it's described in this presentation, but you can find this in our publication. Then we use orthogonal lithography to pattern the polymer. And you can see here also the finished device in the image G, and in image H and E, which is pretty interesting, you can see the substrate before and after releasing the strain. So actually you can see in the figure I, the fact that if you release the strain, you obtain this wrinkle structures, that it's actually the key to achieve the stretchability. Again, this is just to show that we still obtain transistor characteristics, and not as good as a transistor in more conventional substrates, because one of the problems we have with elastomers is that there is some release of contaminants from the elastomer to the active materials, and this leads to a little bit lower on-off ratio with respect to what I've shown before. Then, of course, the devices I have shown you just here, they are made, you can see here, they are pretty small, so the channel length is about 10 microns. So for this kind of device, it's a little bit difficult to do mechanical tests because of the fact that the channel is very small. So, but to prove that this device were actually stretchable, what we did, we made much larger devices. And what we did in this case, we used the same approach to make them. We changed the architecture a little bit. We made all the components planar, as you can see here. So the gate in this case is planar, and it's made also of conducting polymers. And also for the electrolyte, in the previous case, we had just used the water-based electrolyte like sodium chloride. In this case, we used an ionic hydrogel, which is also a stretchable material. So what we did here, we made all the components stretchable. Because what I forgot to mention is that even gold, when it's deposited on a wrinkled substrate becomes stretchable. And we made a device which is actually stretchable. You can see here the characteristics. Here it's a device which is operated at 0, 15%, or 30% strain, and you can see here that the performance are pretty much the same. I hope I'm able to show here how we characterize this device. So you can see here our Tensile Tester. What you see on the top is the hydrogel, which you can see it stretches together with the rest of the device. Here you don't really see the organic semiconductor because it's transparent. You can see the gold source and drain, but you can imagine that in between the source and drain and below the electrolyte, there is the PSS films. Oh, sorry.
Fabio?
Yeah.
Okay.
Okay, I'm sorry. So as I said before, is that what I have just shown was the substrate backlink, but we also can achieve this stretchability by tuning the thickness of the sample. So in the previous slide, I have shown that you can actually achieve different stretching, different change of the current by tuning the thickness. And actually, the key is that when you change the thickness of the material, you affect the mechanical properties of the film, because we are still looking into that. We know that the Young modulus of the film changes by the thickness, and probably by reducing the thickness, you have better matching with the Young modulus of the substrate. So you can see here that if you reduce the thickness, these are just this is the optical images of P.PSS film on PDMS. You can see that if you reduce the thickness, if you apply a certain strain of the to the material, what you see is that if you reduce the thickness, you observe less cracks in the film at a given strain. And the same happens if you don't have much freedom, but the same happens if you reduce the baking temperature. Of course, we need to, I didn't talk about this, but when we deposit P.PSS films, since these are water suspension, we need to heat at about 100 degrees to remove the water. And what we observed is that if we keep this temperature as low as possible, we can also reduce the cracking that happens when we stretch the film. So this brings me to another concept, the fact that these films are actually intrinsically not really flexible and stretchable. They are rather brittle, but the properties of these films can be strongly affected by the processing. So again, this is the results we obtained by tuning the thickness of the material. So again, the fabrication methods are very similar to what I've shown before, but what you can see here again, the transistor characteristics are much better than the ones shown before, because what we did in this case, we also used an intermediate layer between the elastomer and the organic semiconductor. We put a very thin parallel layer that actually prevents the diffusion of contaminants and keeps the on-off ratio high. So it's still not an on-off ratio similar to what we got on PET or silicon substrate, but it goes from a few to about to less than 10 to about 100. So another approach, which is probably the most interesting, is to blend the material with the plasticizers. So in this case, we use a polyethylene glycol plasticizer added directly to the water formulation of PDOT, and we process this into films. So what we got here is pretty interesting, especially if you look at the graph on the right, when we measure actually the change in current upon strain. So you can see that if you look at the blue points, you see that if we have polyethylene glycol added to the PDOT formulation up to about 60%, we observe very change in current. The delta I on the right tells you the change in current with respect to the current of the unstretched substrate. And this actually allowed us to make, again, very stretchable devices. Again, the key is the formation of cracks. And what is very interesting in the case of mixing with the polyethylene glycol is that even if we keep very high film thickness, which is actually an advantage to achieve good performances, we don't observe cracks in the film. So you can see here that almost up to 50%, 45% in this case, the films are crack-free. This is thanks to the presence of polyethylene glycol. So even in this case, we could make stretchable devices by using hydrogel electrolytes. And again, we had pretty good performance. You can see here on the left, the device structure, the white square you see in between the source and drain electrode is actually a stretchable hydrogel. And you see here the device performance that are even better than the ones that we have shown before, because we can stretch more. Before, we could stretch a device up to 30%. Now we can do it up to about 50%. And what is also interesting is that, and this is a topic we are working on, is that the presence of the polyethylene glycol additive can also improve the ionic transport by leading to a higher switching speed, even if we increase the thickness of the device. So now I move to probably the most interesting part, which is the healable electronics. So we have achieved a different, we actually using PDOT PSS or other PDOT formulations, we achieved several self-healable electrical films. And one of our works has been just recently published in Advanced Functional Material. So here the inspiration is again bioelectronics, because we know that many biological systems are healable. For instance, also our skin is partially healable. Unfortunately, not all our organs are healable. And there is, it seems, in nature only one animal which is able to heal all parts of its body, and it's the axolotl, which is an animal which lives in a few places in Mexico. And apparently, even the legs of these animals are healable, and also apparently parts of the brain. So it's a good inspiration for our work. So why we want to have self-healing electronics? Because we believe that it's also a key for sustainable electronics to have materials that can repair by themselves without need of replacement. Of course, it's a little bit a dream, but it's a kind of true. Then also in bioelectronics, sometimes we have materials that are difficult to access. For instance, if we implant them, and it would be, for instance, an advantage if these materials can heal by themselves in an aqueous environment. Then when we started this work, the self-healing conductors were still rare. This is also probably the case now. And sometimes the mechanism for healing is very complicated. So you need to change the processing, to work at high temperature, and to use very complicated solvent. That's why we are looking for something that could be healed in water or just without any external intervention. So this was a work that we did about 3 years ago. So by working in the lab, we realized that the PSS films, if left for a long time, they became like a gel. And we had the idea that they could also have some of the mechanical properties of the gel if we put them in contact with the water. So we did a very simple experiment. I hope the video will work. So it's the image on the right. So we made the strip quite thick. That's still our point. These films are pretty thick for the moment. So the black strip here is a PSS film, and we made it as part of the circuit where we are powering a light emitting diode. So then we simply cut the material with a blade. And what you can see that as soon as we put water into the cut, the lead slits again. And what you can see, what happens here, you can see better on the left part of the graph. You can see here that when you cut the material, the current drops almost to zero. Then when you add water, the current goes back to the initial value. And what is interesting here is that the process is repeatable. So you can cut as many times as you want, and you will always see this healing effect. So in the curve here, you can see this for 3 times. And what you can also see is that the process is pretty fast. So it happens in a few milliseconds, in a few tens of milliseconds, which is also very important because there are cases where healing in these electronic materials needs days to take place, or hours. So what is the key here is actually once we obtain the result, we had a look at the region of the healing, and you can really see that after you cut with a blade, then you see a clear scar in the material, but after you put the water, actually you see that there is material in between the 2 parts of the cut. So that's really a healing effect. We are still looking for the mechanism, detailed mechanism of this, but what you can clearly see here is that the material is there. Again, we looked at the response, so the time, and you can see, as I said before, that the process is very fast. It's about 150 milliseconds, and it doesn't depend on how many times you cut the film. Of course, this is also a function of, of course, what is interesting also is to be able to heal material of different thickness. Now we are going at a very low thickness. And you can see again here that the time does not depend on the thickness. We also looked at several liquids just to be sure that it was not like a physical effect of moving materials. And we take the most inert liquid for our system, which are fluorinated solvents, and we didn't see any effect on the healing. We used some alcohols, and we observed a weak effect, but the solvent that works best is water. So what is interesting also to see how this material reacts to the vapor environment. We did the experiment in a humidity chamber where we changed the humidity, and actually what we saw here is that after the cut, if we at some point we reach 80% relative humidity, we can also see the healing effect in the presence of water vapor. So again, what we did more recently, we tried to change. What I've shown so far was just on pristine PSS films. Sometimes we add the materials to improve the conductivity, but we didn't work too much on the formulation. What we did more recently, we again started to use polyethylene glycols to see if we can improve the healing behavior of these materials. So here we have the experiment for with the polyethylene glycol. It's very similar to what I've shown before, but what is remarkable in this case is that when you cut when you cut the material, you don't see any effect at all. So the material heals by itself. We have I didn't talk about this, but we had observed this behavior in wet films. So if we soak films in water and then we cut, they are, let's say, autonomically healable. But this can be achieved also on dry films that are actually processed in presence of polyethylene glycol. So that's quite remarkable, autonomic healing. And you can see again here the characteristics, the current versus time. Before you could see a drop of the current to 0, and then this would recover where you would put water. In this case, you can see that the recovery is pretty much instantaneous. You see here the moment where we cut the material, sometimes we do see a small drop in the current, sometimes we don't see anything at all. And these two plots are just to say that we can, so the lower plot, the black one, is about pristine, repeated PSS, polyethylene glycol films. The other one is when we add also glycerol to improve the conductivity. So this means that we can also achieve high conductivity and still having autonomic healing. Again, here on the left, you see the differential calorimetry of the material. And what you can see here, this is just to say that if we add some polyethylene glycol in the film, it doesn't evaporate during the processing because it's quite high boiling point. So the polyethylene glycol is still present in the film, and actually it gives it these interesting mechanical properties. Again, in terms of mechanical properties, we try to characterize them. So okay, so another thing we did, even in this case, we looked at SEM. And you can see here on the right, this SEM image after the cut. You do see that there has been a cut in the material, but the two parts of the material, they are merged before doing anything else. And again, on the C, you see the time scale. And again, you see that the process in this case takes place in some tens or hundreds of milliseconds. This strongly depends on how we cut the material. We are still using blades. Razor blades. We have done a lot of research on different razor blades. We have used all brands, and actually depends of the brand of the razor blade, on the hand of the people who cut the material. But anyway, the process remains very, very fast. Again, this I don't know if we are able to see. This is a real-time test performed on a scratcher test. So you will see in a minute the blade of the tester that scratches the material. So you can see here we are cutting the material. You can see that actually, you see the cut only in the first part. You don't see the cut while the blade is cutting. That's why it's all dark. So this means that the material actually heals by itself. So this is an image performed from the bottom. It's a bit difficult to explain, but what it's remarkable here is that while you cut the material, you can see that the healing takes place, and you only see the two parts of the material separated towards the end of the cut. So real imaging, then of course we characterize the mechanical properties, and you can see here what you can observe, that by increasing the amount of polyethylene glycol into the material, you observe a different stress-strain behavior. Actually, what you obtain is when you add more polyethylene glycol, you obtain a softer material. So this means lower Young modulus and larger rupture strain. And this partially explains the fact that this material can be self-healable. Then, of course, as I mentioned, we try to obtain healing on the nanoscale. Actually, by using lithography in this case, instead of using the blade to cut, we just created a gap between two films by using plasma etching. You can see here in figure BSC, this is B is let's say a cut induced by lithography by plasma oxygen etching. And in image C, you see what happens if you add water. So actually, we are able to heal gaps of about 5 microns, even if they are not created by a blade manually. This is quite remarkable because when we do this process, we actually, from the chemical point of view, it's not exactly the same thing of cutting a material by a blade. I believe that when we treat material with plasma, we also change a little bit the chemistry of the process. So again, if you add water to such a system, you can obtain an increase of current. So it's a healing phenomena, even for lithography-induced cuts. Then we also tried to, I will have just a little time for that, we tried to change the formulation. For instance, we used the cross-linkers. In this case, we obtain a more rigid film structure, and we see what we are expecting. So in this case, the healing effect, when we induce, for instance, when we put silane in between, when we add silane into the PSS formulation and we make films, we observe films that are more difficult to heal because of the fact that probably the structure of the film is more rigid. And if we increase the concentration of these cross-linkers up to a certain amount, then the healing is very inefficient. And then we looked at something very interesting, which is the swelling ability of the film. So you can see here that if we add this silane, there is very small swelling of the film when we overcome a certain concentration. Again, the same thing, we could soak film into acid. This is an operation which is often done to increase the conductivity of the film. Actually, can increase the conductivity of orders almost 100 magnitude by using soaking into sulfuric acid. And we observe here again that healing is very inefficient. It only takes place if you add water. And again, even in this case, what happens, we soaked the film in acid for 3 days and we didn't observe any healing. And this is because the film does not undergo any swelling after this treatment. Then we tried other dopants. So we moved away from PSS. We made films with tosylate, triflate, and perchlorate. And again, we observed healing with organic dopants and no healing with the inorganic dopants. In the case of inorganic dopants, the film was done by electrodeposition. In the case of organic, we just did our polymerization. I think that's my last slide. So the main message is that self-healing of PSS films is possible. The healing mode can be controlled by the concentration of molecular and the molecular weight of additives. There is no need of fillers or harmful solvent. The process is at room temperature and the films are very easy to obtain. Now we are also trying to print the film. And also we can achieve the process for films at high conductivity. And in terms of mechanism, we do believe that the key is the change of the mechanical properties for autonomic healing and swelling phenomena for films that are healed by water. I think what I have to do is just to, at this point, acknowledge the funding agencies that made this work possible, and you for your attention and for inviting me to this conference.
So Fabio, thank you very, very much for your inspiring talk. I guess now we are running out of time, but maybe there is time for one question if Carlos has some. Okay, one question.
Yes, there is one quick question. Dominic Pret said that he's not sure he has understood the mechanism for healing. Can you say a few words?
Yeah, we are still working on the mechanism. So we have two kind of healing. So one is the healing induced by water. And in this case, we believe more and more that the key is the swelling. So we have two parts that are separated after the cut. Then we add water, the volume increases, and then the two parts touches. And this is, we observe this because when we remove, for instance, the PSS from the material, or when we cross-link the PSS, which is probably the part that swells in water, then we don't observe this healing. The autonomic healing probably depends on the fact that when we add the polyethylene glycol, we obtain a viscoelastic material. So in that case, the key is the change of the mechanical properties of the material. Very simply, we can obtain a softer material, which actually, when we cut, it moves by itself, as I tried to show with the real-time imaging.
Okay.
Okay, one more question. Once you add water and it heals, if you let it dry, does the heel re-break?
No, the healing, once it's healed, even if the water evaporates, it's still there. We tried this, we waited for evaporation of water, we heat it, but actually once it's healed, it's healed. It's not because the water is there. And again, as I showed in the graph, the current is electronic, it's not ionic, because otherwise we would not see the current flowing into the circuit.
Okay, Fabio, thank you very much. So,
you're welcome.
thanks again, and we can move.
Francesco,
Yes.
before moving to the next speaker, just let me ask one of the attendees, Esther, to add her last name to the participant list. Or maybe she can tell me by the private chat her last name and I can rename.
Okay. So we can move to the next speaker. Actually, next speaker is Dominic Prete from Male, and it is a regular talk. The title of the talk is Mobility and Carrier Concentration in Electrostatic Indium Arsenide Nanowires. So Dominic, the stage is yours.
Okay. Can you?
Yeah, we can hear you.
Okay, perfect. Let me share my screen. Okay. Can you see the presentation?
Yes, we can.
Okay, perfect.
Can you increase the volume a bit of your microphone?
Volume.
You can.
I had some problems with my microphone. I can try audio settings. Is it better like this?
Yeah, much better. Okay.
Okay. So let me get my pointer. Okay. Good morning, everybody, and thank you very much. I would like to thank the organizers for allowing me to give this talk today. Actually, it's very funny as Professor Mikulic in his first talk actually mentioned some of the mechanisms I will be talking about today. Indeed, what we've done is to explore, to characterize the effect of ionic liquids for the electrostatic doping of indium arsenide nanowires. So I don't have to mention to you here that chemical doping, the chemical impurity doping, is ubiquitous in science and technology for several research fields, such as information and communication technologies, as well as energy, just to give for 2 examples. But what happens in the latest years, because we need more and more computational power for processors and stuff like this, we need to put more stuff in less space. And this led to the nanosaturation of semiconductors. Now, at the nanoscale, there are some issues related to chemical doping, which are related to several causes, which may be random doping fluctuations, dopant concentrations, which have to be above the solubility, and thus limiting channel and contact resistances, as well as the chemical doping of a novel class of semiconductors, which are the wide bandgap semiconductors, is a bit difficult for these materials. In this frame, a possible solution is provided by a novel mechanism. Well, I wouldn't say novel, but a novel application of something which is already known, which is the electrostatic doping. Electrostatic doping here, it is really different from the concept of chemical doping, as first of all, it is completely reversible. It is relying on the application of electric fields rather than the insertion of chemical impurities in the crystal lattice of the material. Indeed, the electric fields induce band bending of the semiconductor near the surface where the electric field is most, I would say, felt by the charges in the semiconductor. And this band bending, depending on the relative position of the extrema points of the conduction and valence band in the semiconductor with respect to the Fermi energy level, may lead to the accumulation or depletion of charge carriers in the active channel. I should mention here that this concept of electrostatic doping is much more performing when it is applied on nanostructured materials. Indeed, let's consider a planar conventional MOSFET structure. If the bulk of this, if the extension of a bulky semiconductor is much higher with respect to the extension of the space charge region, which is induced by the band bending effect, so the electrical properties of the material are not really influenced by the application of the electric field. On the opposite hand, if we apply, if we consider a system in which the dimension of the semiconductor is of the same order of magnitude as the extension of the space charge region, so it will be much more effective as the injection of charge carriers. Moreover, this performance is even enhanced, I would say, with the novel low dimensionality nanostructures such as nanowires or fins, which are employed for FinFETs. Indeed, by providing data all around on these materials, it is possible to somehow take advantage of the lower dimensionality in order to improve the effect of electrostatic doping. Our proposal was to employ ionic liquids for electrostatic doping of indium arsenide nanowires. In this slide here, I've shown you a prototypical view of a device. Basically, we have an indium arsenide nanowire, which is contacted with two ohmic contacts, which basically acts as a source and drain contact for measuring the current flowing through the transistor in this configuration, as well as a counter electrode voltage, which is used to polarize the ionic liquid in order to apply the electric field. Now, also again, Professor Mikulic has really in a brilliant way explained how the mechanism of the ionic liquid, of the electric double layer gating works, so I will not stick here with repeating what has already been said, but indeed the choice of ionic liquid in this case is due to the really promising performance for what regards the intensity of the electric fields which are accessible with this kind of gating technique. Also, our devices are provided with conventional P-type silicon dioxide backgate, which is used to probe the doping regime. In this sense, again, also Professor Mikulic has mentioned it, that this kind of systems can be used in the so-called set and freeze operation. So basically, you apply a counter electrode voltage so that the ions are distributed along the surface of the nanowire. The electric field is applied, the band bending occurs, and the electrostatic doping regime is set. What we do next is we cool down the system so that we can apply backgate voltages without having any spurious contributions to the ionic arrangement due to the backgate. In this way, we can probe the electrostatic doping regime by performing electrical transport measurements by employing the backgate. Now, getting to what really happens in our system, let's think about if we apply 0 volts to the counter electrode. What happens is we have no specific ionic accumulation at the interface between the electrolyte, so the ionic liquid, and the nanowire. In this case, what we recover for what concerns the energy band diagram of the material is a conventional indium arsenide energy bands alignment. I should mention here that here I've depicted an N-type semiconductor with a slight downward band bending. This is due to indium arsenide native properties. Indeed, indium arsenide features Fermi-pinning in the conduction band due to surface states, and this leads to even in undoped indium arsenide to this downward bending and N-type behavior. if we apply a negative counter-electrode voltage, what happens is we induce an ion accumulation at the surface of the nanowire, and thus we apply an electric field which has the effect to perform upward band bending, thus depleting the carrier concentration which is sitting there in the pristine regime. On the opposite regime, if we apply a positive counter-electrode voltage, what we are inducing cation accumulation at the interface between the ionic liquid and the nanowire, and thus causing a downward band bending, which is increasing, which is enhancing the electron concentration, and thus we will refer to this as an enhancement doping regime. How this results in proper measurements is reported here in this slide. These three color plots report the measurement of the current by sweeping the drain source voltage and the backgate voltage. I should state again that this measurement has been taken at low temperature, where the ionic liquid is frozen, and so the doping regime is really fixed in the three regimes I was mentioning earlier. So at the first glance, the main difference between the pristine regime and the two extrema of the electrostatic doping regime is the shift of a pinch-off of the pinch-off voltage. So basically, if the pinch-off voltage in the pristine regime sits around -15 volts, for in the depletion doping regime, this value is shifted to around +5 volts. This is compatible with the depletion doping regime we are observing. Indeed, it is necessary to apply a positive backgate voltage in order to allow electrical transport in the nanowire. On the opposite end, for the enhancement doping regime, this pinch-off voltage flies down to around -90 volts. And again, this is highly compatible with the concept of enhancing the carrier electron concentration, as it is needed a really strongly negative backgate voltage in order to quench the conductivity of the system. Now we extract from this measurement, we extract relevant parameters such as the slope of the linear regime in the transconductances curves and the IVDS curves. And by employing these values and employing these formulas reported here, we can extract the parameters which mainly characterizes the doping regime, which are the carrier mobility and carrier concentration. Several interesting effects may be observed. Now consider this plot. Here, the purple curve is showing the measurements for the carrier concentration, while the green curve is reporting the measurements for carrier mobility. Let's talk about for a second carrier concentration. It is the first thing it is possible to notice is that the enhancement doping regime is really much more effective with respect to the depletion doping regime. Indeed, there are two orders of magnitude separating the value of the carrier concentration in the enhancement mode with respect to the pristine doping regime, rather than less than a factor 10, which exists between the carrier concentration in the depleted electrostatic doping regime and pristine regime. This effect, this asymmetry, I would say, could be ascribed to the features of indium arsenide. Mainly, I'm referring to the Fermi pinning in the conduction band due to surface states. Indeed, this Fermi pinning and the native downward band bending of the which is provided by the material of this experiment lets us really easily pull down the energy bands so that we can enhance the carrier concentration, but on the other hand makes it really hard to deplete, to completely deplete and ideally generate an inversion layer in the material. On the other hand, for what regards mobility, what we have is a detrimental effect on mobility both in depletion and enhancement mode. This detrimental effect may be ascribed to several factors, mainly our guess is that the main cause of this detrimental effect on mobility is ascribable to the ionic liquid, to the ions sitting at the interface of the nanowire, causing Coulomb scattering of the charge carriers and thus decreasing the mobility. This issue may be addressed in, I would say, two different ways. A first way would be to change the cation of the ionic liquid by employing a cation which has a longer arcing length. A second possible solution would be to introduce a dielectric spacer, which is basically spatially decoupling the ionic liquid with the nanowire, and in this way, actually in both these ways, for sure, the Coulomb scattering will be reduced, so there will be a less detrimental effect on mobility of charge carriers. But I should mention that this would also reduce the capacitive coupling of the ionic layer with the charge carriers, with the semiconductor, and thus we will probably not observe such a strong effect on the modulation of the carrier concentration for the electrostatic doping. So to conclude, let me summarize briefly what I have presented you. I hope I've convinced you that electrostatic doping is a really promising tool for the next generation semiconducting devices in which the doping is not accessible anymore via conventional chemical impurity doping techniques, and that in this frame, ionic liquids and electric double layer gating in general is a really powerful, promising tool to perform electrostatic doping on semiconducting nanostructures. I've shown you that there are some really strong effects for what concerns carrier the changes on carrier concentration, and also that there are some detrimental effects for what regards the induced carrier mobility for different electrostatic doping regimes, and that these detrimental effects may be issued by employing some changes in the experimental methods. But in general, I believe that these issues, these features of electrostatic doping should be taken into account when designing an experiment in which electrostatic doping is involved, mainly also for low temperature transport measurements in which these parameters are really fundamental for the outcome of the experiment. Let me just very briefly tell you about what we are planning to do next. First of all, by employing surface photovoltaic optical spectroscopy techniques, it will be possible to measure the effect of the electrostatic doping by experimentally measuring the energy bending which we are inducing by employing the ionic liquid gating. Also, exploiting other ionic liquids and semiconductor combination would be very interesting. For example, employing a material which is not providing this Fermi pinning in the conduction band, such as indium arsenide does, so that we can induce not only depletion of charge carriers, but also generate an inversion layer. So we can fully control the electrostatic doping both for n-type and n-type electrostatic doping regimes. And finally, also providing a spacer which is separating the electrolyte and the semiconductor for analyzing the effects on the mobility and carrier concentration would be a very interesting next step to perform. So to conclude, let me thank all the people who made this work possible, that we have worked daily. And most importantly, I would like to thank you all for your attention.
So, Dominic, thank you very much for your nice talk. Again, we have time for, say, 1 to 2 questions, and I guess there is a question already. So, yeah.
Yes, there is a question from Daniel Majidi. Could you please say some words about contacting nanowires? Did you use argon ion milling to remove the oxide layer prior to deposition of metal?
Yeah, no, the contacting ceramic contacts of indium arsenide nanowires has been performed by employing a passivation solution based on ammonium sulfide. So basically we have this pacification solution. We dip the nanowire after the development, after the EBL, basically. After the development of the EBL, we dip the nanowire in this solution, which etches the native oxide of the nanowire.
Oops, yeah. Dominic?
See, yeah?
Still with us, yes, okay, you get frozen.
Ah, sorry, actually it appears your connection is unstable, but I'm here.
Okay, there are two more questions, but I would like to ask Dominic to answer in the chat room.
Oh, okay, okay.
Because actually we are a bit running out of time.
Okay.
Thank you again, Dominic. So now it's time to go for the very last invited speaker of this session. He is Shinpei Ono. Shinpei is from Central Research Institute of Electric Power Industry, Yokosuka, Japan. And the title of his talk will be Development of Iontronics, Application for Energy Harvesters. So Shinpei, you are with us? Yes, and the stage is yours.
Okay, thank you very much. I'm Shinpei Ono from Central Research Institute of Electric Power Industry. And today, I would like to present the development of the Iontronics and the application for energy harvesters. So this is in collaboration with CNRS in France. So we are working on the for Iontronics devices, such as field effect transistors, or spintronics devices, or light emitting electrochemical cell. And today, I want to introduce a new concept of the electric double layer called the electric double layer electrode. Electrode is a permanent charge. It is similar to the magnet, but we are going to fix the motion of the ion inside the polymer networks to make a form electrode. And we are going to apply this electrode to the vibration energy harvester as well as field effect transistors. So recently, the vibration energy harvester have been extensively investigated to realize the alternative energy source to the batteries. So to achieve the trillion sensor universe, there's a strong need for the batteryless sensors. Because if you want to change the put a trillion sensor to all the infrastructure or human body, but we also need to change the batteries. So for these reasons, we are trying to combat the vibration from the infrastructure or human motion and so on to the electric energy enough to operate sensors and send signal to the internet. However, and this is a complex concept. So since, as I said, I'm working on the Central Research Institute of Electric Power Industry. And of course, we are going to electric power industry create a megawatt of the energies. But in our work, we are going to put the milliwatt energies. So it is picking up the seed from the ground, but it is useless before. However, if you want to monitor these infrastructures, we need to create the energy from low frequency vibrations. For example, if you want to, if you see the vibration from the bridge, the resonance frequency is around 15 Hertz. And also, if you see the trucks, the resonance frequency is around 10 Hertz. And if you want to create the energy from the motion of the human motion, it is around 4 Hertz. So we need to develop the energy harvester which create energy from low frequency vibrations. However, it is still difficult to gain energy from low frequency vibrations less than 100 Hertz. Why it is difficult? So if you want to create energy from low frequency vibrations, there's 3 ways. One way is using a piezoelectric material or the electric static materials. The both ways, we need to use very thin beam and the large mass to gain the energy from low frequency vibrations. But if you make this structure, because it is a thin beam and the large mass, so it is very fragile to use this kind of the energy harvester. The other way to create energy from low frequency vibration is using a triboelectric effect materials. But in this case, we need a large force to create energy, enough energy. So to overcome this problem, in this work, we are going to concentrate it to the electric static energy harvester. This is a schematic picture of the electric static energy harvester with electrode. So this is here, this blue one is electrode. And this is electrode, right? So if you insert the electrode to the electrode, the charges are induced at the surface of the electrode and with electric static effect. So if you push and pull this electrode, we can create the energies. And this method is fit to the MEMS technology and like this, because we want to enhance the surface area. And using MEMS technology, we can make a very tiny structure and to enhance the surface area. And also using a MEMS technology, we can also design to the thin beam and the large mass like this to create energy from low frequency vibrations. But to enhance the gain of these devices, there are several spaces to improve. Because this is, again, the simple structure of the devices. Here is the electrode. So if you push this electrode, of course, due to the electric static effect, we can create the energies, the electrons, induce electrons. But the thing, usually, this gap between the electrode and the electrode, this part is air or vacuum. So if you want to enhance the capacitance and the total carrier, which can induce at the interface of the electrode, we need to convert this air to the vacuum. To enhance the capacitance, we are going to use the electric doubler of the electrode. Of course, it is needless to say that when we sandwich the electrode with two electrodes and apply the voltage, the electric doubler are formed after ion distributions. When we zoom in the interface between the electrolyte and the electrode, the electric field is confined only to the electric doubler with thickness around the 1 nanometer, depending on the size of the ions. So if we apply the 3 volt to the system's electrolyte, the electric field at the electric doubler becomes 30 megavolt per centimeter. Using this extremely high electric field, the high density carrier up to the 10 to the power 15 are induced at the surface of the electrode. So we are going to use this electric doubler to in between the electrode and the electrode. So there are several work have been done using mercury droplet or the water. But of course, it is needless to say that these materials, the capacitance of the electric barrier is not enough. So we try to use, instead of the mercury or water, we are going to use ionic liquid. And then this is a picture. So by using changing, giving motions, vibrations to the electrode, we can change the surface area. And by changing surface area, the carrier is accumulated and the electron is moving back and forward. So using this structure, of course, we can enhance the total carrier accumulated at the electrode. But still, we need to apply the voltage to sustain the electric barrier. So it is not a good idea because we want to create energy from the vibrations. But at the same time, we need to apply the voltage to sustain the electric barrier. And also, another problem is using ion liquid is like this. So in the beginning, we try to put the ion liquid on top of the silicon electrode here. But due to the electric static force, the ion immediately attached to the surface of the electrode, and so we cannot change the surface area efficiently. So to change this structure, we are going to use the ion gel instead of the ion liquid itself. Indeed, by using an ion gel, we can efficiently change the surface area. So using this, so in the beginning, this blue line is the position of the electrode. But we can only create a small energy because we can only modify the surface area. But using this ion gel, we can enhance the change of the surface area, and that we can create a higher energy. But still, in any case, we need to use the electrode for this. So then I have a new idea to fix the ion to form the electric barrier electrode. So how to make electric barrier electrode? So we are going to use ionic liquid with unsaturated bond on the cation and the anion, cation and the anion. And also we are going to mix with the polymer, which have several unsaturated bonds. So then we first mix this ion liquid and the polymer, and then after we apply the voltage, the electric barrier are formed. And then we shine the UV light to polymerize these ions inside the polymer networks. And then we can chemically connect the ion liquid inside the polymer networks. And this is an electrode, what we call the electric barrier electrode. So it is, this is the polymer. So it is like a soft shell, but the surface is charged positively and negatively. So for example, it is similar to the magnet. So of course, when we try to attach the cation side and the cation side, and then is ion gel have a strong repulsion. And when we try to attach the cation side and the anion side, and then this polymer is strongly attached. So we can really feel that this electric barrier are fixed to form the electric barrier electrode. Using, and then, as I showed you, this is a fabrication process. So we mix the polymer and the ion, and then there are sandwiches with the two electrodes. But to shine the UV light, one side, we are using an ITO electrode. So and before the irradiation of the UV light, we can see that if you apply the voltage and the electric W are formed, and then it is the current itself is saturated close to the zero. And then if you apply the opposite directions, and then again the ion is moving like this. And then we again apply the another positive opposite directions, and then the current is flowing like this. But once we irradiate the UV light, the ion is almost fixed. So here, the current, total current which flow is around 10 to the power of -3. But after the irradiation of UV light, it is around the order of the -7, 10 to the power of -7. So we believe that more than 99% of the ions are fixed into the polymer networks. So using this electrode, we are going to fabricate the vibration energy harvester. We sandwich its electrode with 2 electrodes, and then we attach and detach the electrode. Electrons are induced at the electrode. So when we touch it, the electron is moving this way, and when we detach the electron is moving this way. Since the capacitance of this electric W electrode are huge, it is similar to the electric W. The large current are accumulated at the surface of the electrode. And this is a demonstration of vibration energy harvester. So when we here is electric W electrode. So when we touch and detach, and the current is flowing the opposite direction, and we can see it of the blinking of the LED light, and which is different directions. So when we touch it, and the electron is moving this way, and when we detach it, electron is moving this way. Some people, this is also the expansion setup, and we can see that electrode is here, and we are touching and detaching this electrode to the electrode. Some people might ask us, is it a really electric static effect or not? Because of course, we are using ion gel. It also creates the piezoelectric effect. So to prove that there's an effect of the electric W, we are going to show this data. So left-hand side, the cation is upper side, and the right-hand side, anion is upper side. So when we and this blue line is the position of this electrode, and here the electrode attached to the electrode. So if you see this here, there's several peaks, and then here we can see that electrode is detached from the electrode. So in the case of the cation side, is on top, and we can see the negative voltage. And if you flip it, and then when we detach it, we can see the positive sign. So this is one proof that indeed we can see the electric static effect of this electric W electrode. Another proof is that if you zoom in this current here, it is like this. So here, electrode is closing to the electrode, and here here is when the electrode attached to the electrode, and before electrode attached to the electrode, we can see some current like this, and here the electrode attached to the electrode, and we can see several signals. And we believe that this part, what we observe is the electric static effect. And this part here, this part, actually the when we electrode attached to the surface of the electrode, we are pushing, and we can see the motion of the electrode. And then depending on this motion, we can see the different sign of the current. So we believe that this part is coming from the triboelectric or the piezoelectric effect. And this part, we only observe the one side. And we believe that this is due to the electric static and the electric triboelectric effect. And also, to prove that, if you, the last one, last one is we are giving, we are giving the 10 Hertz of the vibrations. But if you slow down and the vibration, and also if you use a triangle wave, and then it is like this. Of course, there's some small effect before the electrode attached to the electrode. So there's some current. And of course, it is coming from the electric static effect. But mainly, the current is only observed when we touch to the electrode. So we believe that there's indeed the electric static effects of the electric double layer electrode. And this is another demonstration. And here is the electric double layer electrode, where we touch and detach. And then there we can create the energy like this. So we can easily shine the LED light like this. The average peak power is around 90 microwatt. And if you, divide it with the surface area, it is around 0.5 milliwatt per square centimeter. So if you enhance the surface area, of course, more power is obtained. And the output voltage is more than 2 volt. So it is depends on how much voltage we apply to form the electric double layer. And also, if you use fluorine terminated iron liquid, and this electrode is air stable, it means that we can also use this electrode inside the air, even the very high humidity in Japan. So what we are targeting is we try to make the energy harvester, and now we are working to connect to the circuit to charge to the capacitors. So we want to make this kinds of the battery-shaped devices, which is inside is an energy harvester and the energy storage. So this is one application of the electric double layer electrode. And also, we can use this electric double layer electrode to for the physics. So I'm going to show the one example using this electric double layer electrode. So what we are going to use is electric double layer and directly laminated to the semiconductor devices. So this time I want to show the one side, the cation side is fixed, and the anion side is fully moving. So how to make it is easy, because the cation side has the unsaturated bond, and the anion side don't have the unsaturated bond. So after the formation of the electric double electrode, and then we shine the UV light, and in this case, only the cation is fixed. So we use this kind of electrode and putting on top the STO substrate. And then we are going to show the performance. This is very good because if you are working on the iron liquid gating, usually some people said, oh, this is due to the chemical dopings. And some people said, oh, this is electric static reaction, electric static effect. But it's hard to judge whether it is an electric static effect or chemical reactions. But once we fix the motion of the ions, no current is flowing through this electrode to the surface of the semiconductor material. So we believe that there is no chemical reactions. So we are going to put this film on top of the STO and then to see the performance. And before, we are going to use the gating effect. So when we don't apply the gate voltage, and then the current is not flowing. Of course, this side is flowing, but I'm going to explain later. But no current is flowing because even though we laminate the cation side, but the anion is also anion, which is mobile, is try to cancel out these charges. So there's no channel is formed. But if you apply the positive voltage, gate voltages, and then the anion is accumulating to the gate electric side, and then the channel is formed. So this is green line is after we apply the gate voltages. So just applying the voltage, and then the electron is accumulated at the interface of the STO. But if you see this side, it is like this way. So we don't apply the gate voltage, but still the current is flowing. How can I explain? So if you zoom in this current, it is like this. So when we apply the positive gate, there's no charge carrier injection. But if we apply the negative voltage, what I mean is we apply the voltage between a source and drain, not the gate. So then the carrier is flowing. So if we, what we believe is like this. So if we apply the negative voltage to the between the source and drain, and then, for example, this side is we apply the negative voltage, and then the anion is repulsed from the bias contact, and then the conduction channel is established. So STO become the conductings. So if we don't apply the voltage like this, the anion is moving to cancel this positive charge. And of course, if you apply the positive voltage, the anion is accumulating this way. So no channel, no conductor channel is applied, is shown in this side. So using this electrode, we can operate the transistor with the two terminal devices. So basically, we don't need gate voltage to operate the transistors of these devices. And also, using this electrode, we can see the similar behavior like standard electric W. So for example, this is the result using electric W electrode. So if you don't apply the gate voltage, and then it shows insulating behavior. And then if you apply the voltage, and then we can see the metallic conductions. So even we are using this electrode, the similar data can be obtained, and we can see the metal to the insulator crossover like this. So I would like to summarize my talk. So a new type of the energy harvester with electric W electrode is proposed. So new concept of the electric W electrode, the generate current with an external bias voltage, the large current output current as high as 0. Large output power as high as 0.5 milliwatt is obtained from low frequency vibrations. And also new devices with electric W electrode are proposed. So thank you very much for your kind attention.
Okay. So Shinpei, thank you very, very much for your very interesting talk. I'm sorry my video is, it's still there. And actually, I guess now we have some time for questions. If Carlos maybe has some hints, some questions.
There are no questions yet.
Yes. Okay.
Is there any question?
I just have a curiosity, Shinpei. What about using your system as sort of detectors or sensors for vibrations? I mean, that would be a different approach to the issue, but still interesting. And I mean,
yes.
Is there any perspective of application in this direction, or not?
Yes. So thank you very much for a good question. Actually, indeed, we can make very sensitive sensors. So for example, since we are using this electric W, so small motion, even the small motion give a large current. So for example, when we make this electric W electrode, and some people is moving in the corridor, and we can really see that someone is coming. So it is very sensitive. Devices can be made, yes.
Thank you. Okay, so maybe some other question raise up? Not really. So, Carlos, do you confirm we have no questions?
Yeah, there are no questions, but let me ask one. Is there any frequency dependence to the power output?
So it is, actually, if we enhance the frequency, and then the total current is getting small. So I don't know why, because this is event-driven charge accumulation. Mm-hmm. But somehow there's some degradation of the current using this way, yes, this electrode. I don't know. I still don't understand why it happened.
But Shinpei, did you ever try to really characterize the frequency response of your device, like to plotting a gain as a function of the frequency?
Yes, yes.
What is the cutoff? What is the frequency response?
So actually, it is up to the 1 kilohertz. We can see almost a constant the current. But up to 1 kilohertz, it is going to degrade, shrink.
So 1 kilohertz, yeah, kilohertz. Okay. So, oops. So I would say if there's no other questions, so I want to thank again the speaker. Thank you, Shinpei, for your talk.
Thank you very much.
And yes, so now actually, so there is a change in the program called the speaker is changed because Giovanni Pennelli from University of Pisa could not join the meeting. And so actually I will give the talk on his behalf. Let me try to open the presentation and then share the screen, sorry. Yeah. Okay, so can you see the slide?
Yes.
Yes, okay, nice. So actually, this work, well, the title of the money contribute was Electrolyte Gated Nanowire Field Effect Transistor for Advanced Control of Thermoelectric Functionalities. And the work was done entirely in Pisa and stems from a collaboration between my group and Giovanni group in the University of Pisa. So basically, we both are interested in nanoscale thermoelectrics, in particular nanowire thermoelectrics. And actually, when you deal with a thermoelectric device, whatever it is, macro scale or nanoscale, basically you are always interested in measuring, controlling, and optimizing its figure of merit. So just to remind you, figure of merit is a measure of the quality, of the efficiency of the device in generating power, electrical power, out of a temperature gradient. And basically it is the ratio between two families of quantities. Here you have the Seebeck coefficient and the electrical conductivity, while here at the bottom you have thermal conductivity, basically from the lattice and from electron systems. Okay, so if you look at this very simple formula, what you get immediately is that what you need is device architecture that allow you to both measure the electrical quantities, thermal quantities, and possibly to modulate these quantities by exploiting some tool that can be provided, of course, by field effect. So when it comes to the electrical quantities, so Seebeck coefficient and electrical conductivity, actually you can act very well and do very nice devices if you start from a supported nano object. So you take your nano object, nano wire, nanotube, whatever, flake of graphene, and you drop cast it onto substrate, which is typically some kind of silicon oxide over silicon, so you can use this substrate as backgate, and then you can go for a device architecture that allow you to fully characterize and measure the electrical conductivity and the Seebeck coefficient. This means that you need to build up a device like the one you see on the bottom left of the screen. So basically this is your nanowire. You have to fabricate electrodes at both ends that allow you simultaneously to measure the current across the nanowire, so to measure the IV characteristic of the nanowire, and at a time to measure the temperature at both ends, the hot end and the cold end. And in order to have a cold end and a hot end, you need to establish a temperature gradient parallel to the nanowire, sorry. Yeah, and to do this, well, you can go for a couple of options at least. You can, for instance, to fabricate a heater which is buried and which forces a current to flow in the substrate perpendicularly to the nanowire, so that this current flowing here is creating a temperature gradient in this direction. Or you can very simply fabricate a sort of serpentine made of metal, and by feeding a current into the serpentine, what you get is Joule heating of the substrate, and so again you will create a temperature gradient along the direction of your non-object. Okay, so along the years we have used this approach to demonstrate basically the full electrostatic control of the thermoelectric properties, I mean Seebeck coefficient and power factor, in nano devices fabricated out of individual nanowires. Nanowires, I mean basically 3-5 semiconductor nanowires, like indium arsenide nanowires. And this can be done using simple homogeneous nanowires, where you can go, for instance, for the modulation of the Seebeck coefficient in a wide resistance range, and we also have used more complex nanowire heterostructures like nanowire quantum dots. Actually, if you build up a couple of barriers made of indium phosphide, for instance, inside the body of an indium arsenide nanowire, you can exploit the band engineering in order to create a discretization of the energy states inside the nanowire. You create a quantum dot, and then you can go for exploring the impact of temperature gradient along the nanowire, which result in a temperature difference between the two sides of the dots. So, but apart from this, what we also did was to develop device architectures in order to measure the thermal conductivity in our nano devices. But in this case, while for measuring the electrical conductivity and the Seebeck coefficient, you can go for a object that is drop casted onto the substrate. In this case, if you want to measure the thermal conductivity, you better go for a suspended geometry, right? Because you need to decouple thermally and mechanically your nano object, say your nanowire, from the substrate. Otherwise, you have to face strong losses. So basically, again, you can go for a couple of routes in order to measure the thermal conductivity. You can exploit fully optical approaches, which consist in basically heating locally the nanowire, suspended nanowire, using a laser beam and measuring the temperature profile along the nanowire, and then using some analytical formula in order to extract the thermal conductivity in the nanowire. Or you can go for all electrical method. Well, this method actually is known as the 3 omega method, and consists in feeding the suspended nanowire with a current, an electrical current, picking up the third harmonic of the voltage drop, and from this third harmonic extracting, by resorting to an analytical dependence, the thermal conductivity. So here you see the device architecture. So your nanowire is suspended onto a substrate, and it is contacted with 4 electrodes. The external electrodes are used to feed the current. The internal electrodes are used to detect the voltage drop. And then, thanks to this very simple actually expression, which relates the third harmonic of the voltage drop to the current via some parameters which is known or can be measured, you can get the thermal conductivity. This is very nice. It works very well, and it returns value of thermal conductivity, which is which matches the expectation from theoretical calculations, and we were happy about this. But then the point was that comes to our mind was the following. So we would like actually to gate a suspended nanowire device, because if we want to measure and to control the full figure of merit, we need at a time to measure and to control the electrical properties, so electrical conductivity, Seebeck coefficient, and the thermal conductivity in the same nano device. And this cannot be done if we need to fabricate 2 different devices in order to go independently and separately for the 2 families of physical quantities, right? And unfortunately, by recurring to conventional gating methods, like as I've shown, using the backgate as using the substrate as a backgate, well, what you get in the temperature intervals that can be of interest for thermoelectric applications, so say from room temperature above, what you get is a very poor gating efficiency. We try to play with combination of backgate and even side gates, realized with metallic electrodes fabricated in the very close proximity of the nanowire. We played using together the three or multiple gates, but what we got and what is expected is a poor modulation of the electrical conductivity in the nanowires. Also because when you want to go for thermoelectric application, of course you need to start from a relatively highly doped nano objects, right? So for instance, just to give you a number, what we got was a resistance modulation of say 5 to 15% within a huge interval of gate voltage applied to the combination of gates. So the modulation is very poor, and this is not what we are looking for. What we are looking for is a real strong modulation of the Seebeck coefficient, which allows us basically to modulate overall the figure of merit. And so the question is there any strategy for gating a suspended nanowire device and at a time measuring its thermal conductivity, electrical conductivity, and measuring directly or indirectly its Seebeck coefficient in order to get a fully electrostatically controlled figure of merit? So the answer is yes, and the answer is, of course, you can go with ideal gating or ion gate. The idea here is the following. Basically, you start with your suspended nanowire device that you fabricate using standard EBL and lithography technique, but then you also equip your device with a large counter electrode which allow to polarize a droplet of electrolyte which is embedding your device. As the electrolyte, we use ionic liquids on which we have some expertise already, and we know they are nicely operating with 3/5 semiconductor nanowires. So basically, this is our starting point. So suspended nanowire device equipped with 4 electrodes and counter electrodes, which allows to polarize this droplet of ionic liquids, which is surrounding all the device. And what we want to do is to measure the thermal conductivity, and at the time to measure and modulate the electrical conductivity by using EDL gating, and possibly extract the full figure of merit of the device. So here there is a tricky point that must be mentioned, that is the following. So I said a few slides ago that we need to decouple thermally and mechanically the nanowire from the substrate, but here we have the nanowire fully embedded into a different media, which is the ionic liquid. So why in this case we are happy and we were not happy in having the nanowire broadcasted onto the substrate? Well, simply because the thermal conductivity of most of electrolytes like ionic liquids is several order of magnitude lower with respect to the one of the nanowire and of any standard substrate like silicon oxide. And so basically we can consider the ionic liquid as an insulating system, a thermally insulating system, and it will affect the precision of the measurement of the thermal conductivity in a negligible way. Okay, so once we have this device, the first thing we have to do is to convince ourselves that the device is operating nicely as a EDL nanowire field effect transistor, and we also want to convince ourselves that this device is very robust, so that a potential strain coming from the fact that the nanowire is suspended and is surrounded by a different media, so this potential strain does not detrimentally affect the mechanical stability of the device. So we did a couple of things. First of all, we characterized the operation of the EDL transistor at room temperature or slightly below, but in any case at a temperature above the freezing temperature of the liquid, and we observed how nicely, as have been shown already by a number of speakers, Adam and Dominic as well, so how nicely you can fully open and close your transistor and fully control the level of the conductivity inside your nanowire device. This is can be seen in this current map, which reports the current in the nanowire as a function of the source drain voltage and the liquid gate. And at the time, what we did was taking our here we go, our nanowire device, and applying a number of cycles of cooling and heating. So we measure the device in a set and freeze mode, not just to precisely characterize the electrical response, but most importantly, in this case, for this kind of application, to be sure about the mechanical stability. And actually, mechanically, the device was very, very robust, because it can sustain a number of cycles of cooling from room temperature down to 4K, and still the device is there and still is working. So at this point, what we had was the full electrical characterization, DC electrical characterization of our device operated as a EDL transistor, and the characterization of the mechanical stability of the device. Then we could go for the operation of the device as a system for the simultaneous electrical and thermal conductivity measurement, and possibly for the extraction of the full figure of merit. And this is what we did. So on the left panel, what you can see is a plot of the third harmonic of the voltage picked up in the nanowire as a function of the feeding current. As you see, cubic response is expected, and in fact we measure this cubic response for many different liquid gate voltages applied to the ionic liquid. We were operating our device in AC, of course, and basically the frequency was kind of 10 Hertz, and the injection resistance kind of 100 to 200 kilo ohm. Then, so out of these plots, what you can get is thermal conductivity as a function of the liquid gate voltage, provided you also address experimentally the other parameters of the system, that are some geometrical parameter, the resistance of your nano object, of your nanowire, and the derivative of the resistance as a function of temperature. Okay, so this you can measure. And so this is the resistance as a function of the liquid gate voltage, while this curve with an opposite trend is the derivative of the resistance as a function of the temperature, again plotted as a function of the liquid gate voltage. If you put together all these experimental data, and you use this simple formula, which again relates the feeding current with the third harmonic of the voltage and that you pick up in your nanowire, you can plot the thermal conductivity as a function of the liquid gate. And this is the result of the measurement, and actually it's not so surprising that the value of the temperature of the thermal conductivity is basically constant. We don't expect any strong impact, at least in first approximation, of the ions surrounding our nanowire on thermal conductivity. And in first approximation, we expect to measure a number here, which is slightly lower with respect to the thermal conductivity of indium arsenide in the bulk, because this is a nanoscale system where phonon scattering depends strongly on the small size and on the surface effects, which are due to the high aspect ratio of the device. So at this point, in order to get the full figure of merit of our device, what we did was to use a simple relation between the Seebeck coefficient S and the electrical conductivity. This is the Stratton formula, which relates indeed the electrical conductivity and the density of states, which can be calculated analytically, to the Seebeck coefficient. So extracting the electrical conductivity from our electrical measurements, we got actually the Seebeck as a function of the liquid gate. But now, having the Seebeck measured as a function of the liquid gate and having measured previously the thermal conductivity for each individual liquid gate voltage applied to the nanowire, we could put together this information. Here is the power factor as a function of the liquid gate voltage. Here, and here is finally the figure of merit, which is modulated electrostatically by the liquid gate voltage. So here the take-home message is that you can exploit ionic liquids or other electrolytes in order to go for ideal gating of a suspended nanowire device and measure and extract the full figure of merit, and using the field effect to modulate and to control the figure of merit. And just for completeness, and this brings me to the very last slide of the presentation, well, we actually devote some time in basically reproducing this approach and this protocol, but using a completely different material system, because we have a decent expertise on 3-5 semiconductor nanowires. We always work with 3-5 semiconductor nanowires, but we wanted to be sure that this approach is general, is universal if you want, and you can use this approach for measuring the figure of merit of any high aspect ratio semiconductor, like silicon, for instance. And this is the reason why we established a collaboration with our colleague from University of Pisa, Giovanni Pennelli, who was supposed to give the talk today, and he has a strong expertise on silicon systems at the nanoscale. So we basically went for, we basically went for a similar device architecture, but starting from a bulk of silicon, doped silicon. So with a top view, with a top-down approach, we fabricated silicon nanowire, and then by applying the same protocol that we already developed for 3-5 semiconductors, we have extracted the figure of merit of the nanowire, of the silicon nanowires of this nanoscale device. And so this is the very end of the story. Actually, let me just so these are the people involved in this work, doing measurements, growing nanowires, and synthesizing the ionic liquids. And yeah, so thank you. Okay, so let me go back to the Zoom. Yes, here we go. No, not yet. Carlos, is there any question?
Not yet.
Not yet. Better. Okay. Okay. So if not, I guess we can. Sorry, I cannot see you. Can you hear me?
Yes.
Yes. Okay. Perfect. So some trouble with Zoom, but okay. So so if there are no questions, I guess.
There is one question from Adam Mikoli.
Yes.
The ionic liquid you use, when it solidifies, what's its structure? Polycrystal? Amorphous?
I guess it, well, let me just go for, sorry. So the ionic liquid we use is this one, and as far as I know, but maybe Dominic can confirm, it tends to crystallize below kind of 220, 230 Kelvin. Actually, but about the structure, honestly, Adam, I don't have a precise idea. Maybe I don't know if Dominic has an idea about the crystalline structure of the ionic liquid upon freezing. Since no. So actually, we suspect that this can have an impact, of course, on the action, on the gating action of the ionic liquid onto the nanowire upon freezing. But actually, we didn't go accurately for this point, actually, Adam. Maybe
okay. Dominic has pointed out that it should undergo a glass transition to amorphous.
Ah, okay. Okay. Okay, so now we can, if there are no other questions.
Yes, there is one more question by Mikoli.
Okay.
He was also thinking you can engineer the thermal conductivity in parallel.
Yeah,
and stop it as a loss path.
Well, what we can do, of course, is using nanowires. So in this case, we just took a simple homogeneous indium arsenide nanowires in order to demonstrate the proof of concept now of this approach. But I completely agree. Of course, we could go for more structured nanowires, like for nanowires embedding superlattices, or simply to for smaller nanowires in order to further decrease the thermal conductivity, so we can combine a sort of material engineering at the level of the solid state device of the solid state nano object together with the power of the EDL gating. Yeah, this would be one of the next steps we are going to do in this direction. Actually, there is some collaboration with for instance, the group of Ilaria Zardo in Basel, who has a strong expertise in phononics at the nanoscale, and so we are trying to combine our expertise in order to go for the optimization, not just for the measurement of the figure of merit, but the optimization of the figure of merit. So increasing the figure of merit by exploiting this approach.
Okay.
Okay.
There are not more questions, so I think we can move to the next speaker.
To the very last speaker, actually, of the session. So here is the program. Actually, the very last speaker is Eva Pogna. Eva is from Nest, CNR Nano, and the title of her talk will be gate-tunable ultra-fast response of single-layer graphene with ionic liquid gating. So, Eva, the stage is yours.
Thank you. I'd like to thank the organizers for this opportunity and also all the attendees for waiting till the very last talk of the morning. I would like to talk about an application of the ionic liquid gating to tune the Fermi level of single-layer graphene in order to explore the doping tunability of the nonlinear optical properties. I don't know why it's not... Okay, so this work was supported by the Graphene Flagship and was born within the collaboration between the Polytechnic of Milano, where I perform the ultra-fast pump probe characterization, and the Graphene Center of the Cambridge University, where the graphene field effect transistor was fabricated, and finally with the University of Pisa for the time result simulation of the nonlinear optical response. I believe that graphene needs no particular introduction. I just want to recall the low energy electronic band structure, which is consisting of linearly dispersing conduction and valence band, which are crossing at the Dirac points. And this enables an easy tunability of the Fermi level, which has a square root dependence on the carrier density. Concerning the optical properties, the static absorption and the optical conductivity results from the interplay of intraband and interband transitions. Specifically, intraband transition dominates the response in the far infrared, in the terahertz, and at lower frequencies, and can be described within a Drude model. Instead, in the near infrared, the dipole allowed pi star interband transitions are dominating and give rise to almost constant contribution of around 2%, 2.3% of absorption. The tunability of the linear absorption with the Fermi level has been largely explored within all the frequency range, and this basically exploiting the band filling effects. So the variation with the density of the electronic states available to interband and intraband transitions. For this study, we concentrated in the near infrared range where interband transition dominates, and to see sizable effects, we need to apply and to move the Fermi level up to hundreds of milli-electron volts. Such a carrier injection to reach a density of the order of 10 to the 12 can be easily obtained by ionic liquid gating, as has been described in this morning. Specifically for this work, we use this ionic liquid with, it's better I don't try to read out. We use a field effect transistor with a top gate because we were interested in measuring the optical properties of graphene in transmission geometry. The graphene was prepared by chemical vapor deposition, and it has a large area of about 1 centimeter square. So first of all, we characterize the transport properties of the device, and we can testify for the ambipolar conductance of graphene, which is manifested by the B-shape of the source drain current as a function of the gate. We could also find the charge neutrality point as the minimum conductivity. In this case was reached applying a gate voltage of 0.8 volt, which depends on the choice of the metal for the contacts. And moreover, we could measure the mobility of the sample, which is around 1000. We measure also the linear transmittance. We have a complicated structure. So first of all, we took the transmission of in a position of the transistor where we have no graphene, and we took it as a reference for 100% transmission. We measure the transmittance in this wavelength range. Then we measure the transmittance at the charge neutrality point. You can see that we have the expected 2% absorption. These sharp peaks are related to the absorption from the ionic liquid, whose thickness is not homogeneous all over the sample. And if we sweep the gate, we saw a drastic change of the absorption properties of the material. If we plot the transmittance as at the gate voltage Vg as a reference to the charge neutrality point, we can see a step-like function which describes the cutoff for interband absorption. In fact, above the threshold for the blocking of the interband absorption by Pauli blocking mechanism, the transmission approaches the 100% value. So the graph becomes barely transparent with a residual contribution due to the interband absorption. From the fit of the step-like function, we determine the Fermi level, which with moderate gate voltage of less than 2 volts, reach large values of the order of 800 milli-electron volt. From this plot, we can see that the single-layer graphene in this case has a residual doping at the charge neutrality point, which can be ascribed to charge impurities in the dielectric core at the interface with graphene. So we explored the nonlinear optical properties by performing a pump probe experiments using a pump and probe in the near infrared range with an overall time resolution of 100 femtoseconds. The pump is photoexciting the charge carriers in the graphene, and the probe is monitoring the relaxation of the charge carriers through the modification of the transmission. When the pump is absorbed via interband transition, out of equilibrium distribution of electrons in the conduction band and of holes in the valence band is induced. Those are peaks at half of the energy of the pump pulse. By means of electron-electron scattering, this out of equilibrium carrier distribution rapidly thermalizes to Fermi-Dirac distribution that has a precise and well-defined electron temperature. In this study, we were interested in the subsequent step of the relaxation dynamics, during which the hot Fermi-Dirac distribution cools down to the equilibrium. The probe detects the presence of a hot carrier distribution as an increase in the transmission, so a photobleaching signal. This is due to the fact that the photoexcited carriers are blocking the absorption via Pauli blocking mechanism. The relaxation dynamics of the photobleaching as usually a B-exponential-like functional decay with a fast component which is attributed to the emission of strongly coupled optical phonons, while a slower decay of the order of few picoseconds it's attributed to the anharmonic coupling of the optical phonons with the acoustic phonons of graphene. With this characteristic, graphene acts as an ideal fast saturable absorber. But what is changing if we tune the Fermi level? So we measure the transient transmittivity, which is here plotted at a fixed time delay, and we saw a photobleaching signal. Interestingly, as we increase the doping, we see that the photobleaching signal is increasing. But for further carrier injection, we saw a dramatic change of the signal and eventually a change of sign, which becomes a photoinduced absorption. This means that in the photoexcited case, graphene becomes more absorptive than in the equilibrium. This is true for all the probe, for all the probe photon energies. What is changing is the doping threshold at which we have the maximum of photobleaching and the change of sign. Specifically, the change of sign in terms of Fermi level occurs at the half of the probe photon energy, which is exactly the threshold for Pauli blocking mechanism of the probe. So the explanation that we found for this sign change is that for such high doping, the probe in the unpumped sample is already blocked, the absorption of the probe. So the photoexcitation with the pump can't but freeze and state for interband transition, and thus lead to an increase of the probe absorption. In order to test this idea, we simulated the transient transmittivity signal as a function of the Fermi level, just considering the effect of the modification of the carrier distribution with the doping. And by simply considering this effect, we could reproduce both the initial increase in the bleaching signal and the change of sign. Concerning the relaxation dynamic, also we could observe interesting changes. By increasing the doping, the relaxation dynamics becomes gradually slower, and from a B-exponential-like function becomes a mono-exponential function, such like if the fast relaxation channel is being quenched by an effect. So here I'm plotting the same data, so transient transmittivity as a function of the time delay for two different probe energy. We can see that we have the change of sign at half of the probe photon energy and the relaxation slowdowns. What it changes if we tune the probe wavelength is just the threshold at which this modification occurs. In order to explain the slowdowns, we consider the fact that as we increase the doping, we are saturating the phase space available for electrons to relax by emitting an optical phonons. And in this way, we are gradually quenching this fast decay channel. To test this hypothesis, we again simulate the nonlinear optical response by introducing the relaxation dynamics of the hot electron temperature, considering only two relaxation processes. So the emission of the optical phonons and the anharmonic coupling of the optical phonons with the acoustic phonons. And by simply considering, again, the modification of the carrier distribution, we could describe both the change of sign and the relaxation slowdown. So in conclusion, by an unprecedented tuning of the Fermi level of graphene, we could observe a dramatic change of its nonlinear optical properties. In the intrinsic case, graphene acts like a fast saturable absorber with a fast relaxation dynamics driven by the emission of the optical phonons. By increasing the doping, we can eventually quench this relaxation channel and obtain a slower recovery time, such that the graphene could be applied as a slow saturable absorber. Finally, if we exceed with the doping the threshold for interband transition, we can even reverse the behavior of graphene and obtain a reverse saturable absorber. So with this, I conclude and thank you for the attention.
Thank you very much, Eva, for this brilliant talk. Actually, very interesting. Now we have some time for questions, if any. I'm looking at the chat. For the moment, no question. Meanwhile, I remind you after Eva's talk to turn on your webcam. So we are going to take a screenshot of today's participant. So any question? Well, actually, I have curiosity, Eva. The pump probe characterization of your device you have shown, so was carried out always in transmission, right?
Yes.
So is it possible to adapt the setup in order to operate in reflection geometry? I mean, keeping this pump probe configuration for ultra fast response of the optical response of the device, can you work in reflection geometry like a theta geometry or coaxial? I don't know.
Yes. What I can say is, thank you for the question. What I can say, for example, if you want to have a backgate, for example, in silicon, where which has which does not allow for measurement in the near infrared in transmission, in that case, the response in reflection can be, of course, measured. We must consider that in the cases where we have graphene deposited on silicon substrate, for example, the response will be again dominated by the variation of the transmission, which is double passing through the graphene and is reflected by the silicon substrate. So we will find a very similar scenario. Instead, if you want to monitor the reflectivity changes on a dielectric substrate, which has a low reflectivity, then you will end up to see a response which is dominated by the changes of the reflectivity of graphene. So in that case, you can access to complementary information.
Yeah, that is what I had in mind. So you can assess kind of thermal or mechanical response of the device, maybe, no? By monitoring its I don't know, vibration or changing shape or cross section somehow. I don't know. Just guess.
For sure, it will be more difficult to align. Let's say that's the easiest way to measure. In this case, is in transmission.
Okay, thank you very much, Eva. I don't see any question actually. So yes. So first of all, I want to thank all the speakers for
Let me stop sharing.
The fantastic talks they gave, and so I remind you that tomorrow morning at the same time, so 9:30, we are going to have the second session of the mini colloquium. And yes, I guess we can, if you agree, of course, you can switch on your webcam, and Lola is going to take a screenshot of today's participants for the posterity. So we are waiting for your webcams. Dino, Juan Beltran, Dominic, Maria Douton, Alejandro Gallego, and yes. So, well, a particular thank to the speakers who had to wake up in the middle of the night to join the meeting, like Fabio. And yes, here we go, almost. I see Adam, Ignazio. Few webcam is still missing. But Carlos had to leave, so he apologized, but he cannot be in today's screenshot. So we can wait 1 minute more, and then Lola is going to take the screenshot. Maybe. Okay, maybe. Lola, we cannot hear you actually. Still cannot hear you.
It's because I was capturing the screen, so yeah. I was on a different. So I was telling you that the participants which don't have their cameras on is because I don't think they do have webcams. So I will take the screenshot with just 10 of us, and tomorrow we take another one with Carlos and the speakers of tomorrow and the attendees of tomorrow. Okay? Okay, it is taken.
Okay. Thanks a lot, Lola. Thanks to everybody. And
can you, Francesco, I need to speak with you a minute.
Sure. I will stay. So thanks again. Thank you all the speakers, and see you tomorrow. Bye.
Bye. I can.
Yes, participants.
Yeah, no, they are leaving. Yeah, because there were some that they didn't have a webcam, so.
Yeah.
You can also hide participants which don't have a video. Okay. Anyway, I'm afraid to kick them out.
No, yeah, don't do.
Because then there is some problem joining again tomorrow. Anyway, something really quick. I have seen the program of tomorrow.
Yes.
Is there a coffee break schedule?
No, it's not, but actually that would be maybe a good idea, because I guess we all need at some point to have a coffee. So let me check tomorrow's program. So day 2. No, it's not.
No, it's because it's. I was checking on the app, on the mobile app.
No, yes, I know, I understand. So no, but actually the new program. So we updated the program. I don't know, kind of 1 week ago, and because Carlos observed that there was a gap, but now there is no gap anymore.
fine. That was the thing. It was the only thing I needed to.
Yeah. But actually, to me, would be a good idea to have a coffee break. But now that it's not scheduled, maybe it's, I don't know.
Yeah, also because of the timing. If you want to join or jump to another session, then it's...
Yes, in fact. I'm sorry that we were running a bit out of time, but you know, I mean, we were all so interested and the speakers were great, and I really had no heart to stop them and to